There is a weight to the dark when you're lying still, not a metaphor. The actual pressure of a blanket or a ceiling or just the room's quiet sitting on your chest. You notice it more when everything slows down. When your breathing gets deliberate and your mind stops running from one thing to the next and just stays somewhere. Start there. Stay there for a moment, because the thing we are going to sit with tonight begins in a place that has no analogue in your experience. No frame for it, really. And I want to be careful not to pretend otherwise. Guys, I read your comments, and there is one thing I keep seeing. The voice you are hearing is synthetic, and many of you want a human voiceover. I hear you completely, and that is exactly where this channel is headed. The honest truth is that this channel is fully community funded, and right now we do not have enough Patreon members to make that happen. I am thankful for everyone who is already supporting, but we need more people there to take that next step. It is a small team, 2 part-time contributors and me, building this as we go. If you want to see this channel grow into something with a real human voice, merchandise and actual scientist interviews, supporting on Patreon is the most direct way to make that happen. The link is in the description. The universe, in its first millisecond, was not a place. That is the honest starting point. Not a dark place, not a hot place, not an empty place with things moving through it. The categories we use for places, inside, outside, here, there, did not yet apply in any stable sense. Space was expanding so fast that 2 points which had been touching could become causally disconnected from each other in less time than it takes a nerve impulse to cross a fingertip. What we call distance was being manufactured continuously, in all directions, without pause, and inside that, or rather, as that, was heat. Real heat. The kind of heat that stops being a temperature and starts being a condition. Physicists write it as 10 to the power of 12 degrees Kelvin, which is not a number you're supposed to feel. It is a number you're supposed to note and move past, but try for a moment to stay with what it means. At that temperature, matter as we know it does not exist. Protons and neutrons had not yet formed. The stuff inside protons, the quarks, were free, floating, colliding, recombining constantly, not bound into anything recognizable. Gluons, the particles that normally hold quarks together inside a proton, were also just loose in the soup. The whole early universe was a kind of sticky, furious porridge of fundamental particles, which is a ridiculous way to describe it, and also about as close as language gets. This state is called a quark-gluon plasma, and it is strange because it behaves less like a gas and more like a nearly perfect liquid. Viscosity close to zero, density almost incomprehensibly high. The kind of material that if you could somehow hold a teaspoon of it in your hand, well, you could not. The teaspoon would not survive the neighborhood. Light could not travel freely through this, not because it was being blocked exactly, but because the plasma was so dense that photons were absorbed and re-emitted almost immediately, constantly, before they could cross any meaningful distance. The universe was opaque in the most fundamental sense. There was no across, there was no through. Just this continuous churning presence of energy in every direction, at every point, all at once. Everywhere was the same temperature. That matters. There were no cold spots, no warm currents, no gradients you could follow from one state to another. Mostly the same temperature. And this is where something subtle begins, something that will take a long time to become visible, but that was already, in the first millisecond, doing quiet work. The quantum world does not permit perfect uniformity. That is not a philosophy. It is a constraint written into how particles behave at small scales. The uncertainty principle, the one Heisenberg described, means that a field of energy cannot be completely smooth. It must have fluctuations. Small deviations, random in location and magnitude, appearing and disappearing faster than any instrument we could ever track. In an ordinary setting, in a room, in a laboratory, in the space between stars, these quantum fluctuations do nothing much. They are the background noise beneath the background noise. But the early universe was not an ordinary setting, and what happened to those fluctuations in that first millisecond, in that impossible heat, that is where this whole story lives. That is what we are here to untangle, slowly, over the next few hours. Not the stars, not the galaxies, not the black holes that formed from dying suns, which takes billions of years and requires a whole separate kind of physics, something older, something that was already happening before any of that was possible, before the first atom, before the first proton even, in the plasma, in the heat, in the quiet, statistical jitter of a universe that could not be still. That is where we are starting. The first people to seriously propose that black holes might have formed in the early universe were also the first people to conclude that they probably didn't. That is not a knock on them. Yakov Zeldovich and Igor Novikov were two of the most capable theoretical physicists working in the Soviet Union in the 1960s, which is a way of saying they were among the most capable working anywhere. Their 1967 paper did something genuinely unusual for its era. It asked what would happen if the extraordinary density of the early universe had produced black holes directly, before stars had a chance to form and collapse. They worked through the mathematics carefully, and then they looked at what the mathematics implied and decided the idea was not viable. Their reasoning was, in retrospect, almost correct. They concluded that any primordial black hole would accrete surrounding matter so rapidly that it would grow without bound, eventually reaching a mass comparable to the entire visible universe. Since no such object exists, they reasoned, primordial black holes probably never formed. They wrote the idea off in the same paper that introduced it. A remarkable thing to do, actually, to open a door and close it yourself in the span of a few pages. The problem, which took several more years to identify properly, was that their accretion model did not account for the expansion of the universe. Cosmic expansion actively suppresses accretion. A black hole formed in that early plasma could not simply feed on its surroundings indefinitely, because those surroundings were receding. The universe was not giving the black hole time to gorge. Zeldovich and Novikov got the physics mostly right, but the cosmology slightly wrong. And that small gap was enough to bury the idea for nearly 4 years. Stephen Hawking came to it differently. His 1971 paper was not trying to solve the same problem. He was interested in the lower end. How small could a black hole formed in the early universe actually be? What he imagined were objects almost atomic in scale, tiny, electrically charged, with masses down near what physicists call the Planck mass, roughly the mass of a large flea, in a volume so small it makes a proton look cavernous. He thought they might move through dense material, capturing electrons, forming a sort of exotic atom. He genuinely considered whether you could detect one in a bubble chamber. That specific picture did not survive, but the exercise of thinking about it seriously did. Hawking and Bernard Carr, his doctoral student at the time, published a more rigorous treatment in 1974. This one stuck. They showed that the cosmic expansion does, in fact, prevent runaway accretion, vindicating the original intuition and rescuing the idea from the conclusion Zeldovich and Novikov had drawn. They described how overdense regions in the early universe, regions where the density happened to be slightly above average, could collapse under their own gravity during the radiation-dominated era. Not all of them, not even most of them, but some, under the right conditions, would cross a threshold and fall inward irreversibly, producing black holes of whatever mass the horizon contained at that moment. What followed from that 1974 paper is honestly strange to think about. Hawking had started asking what would happen to a very small black hole over time. If these objects could form with masses near the Planck scale, or even slightly above it, they would be extraordinarily hot by the standards of ordinary black holes. And heat implies radiation, and radiation implies energy loss. And energy loss from a black hole implies something that general relativity, on its own, says cannot happen. So he had to go deeper. He had to pull in quantum field theory. He had to ask what quantum mechanics does to empty space near an event horizon. And what he found there, the result we now call Hawking radiation, is the most important theoretical result in physics from the second half of the 20th century that still has not been directly confirmed. He found it because he was trying to understand what happens to small primordial black holes. Not because he set out to revolutionize thermodynamics, not because he was trying to resolve the tension between general relativity and quantum theory. He was following a fairly specific question about early universe objects that his community was not yet sure even existed. The discovery came sideways, through a door that two other physicists had already tried to close. That is, in my opinion, one of the better stories in physics. Not the tidy version, the actual one. The objects that started all of this, the ones Zeldovich and Novikov waved away, the ones Hawking tried to imagine holding a charge, are what we are here to follow, because they did not stay theoretical for long. The word fluctuation is doing a lot of work in this story, and it is worth slowing down long enough to understand what it actually means. Not the definition you find in a textbook, the physical reality of it. Press your thumb into something soft, bread dough, a foam pillow, anything that gives slightly and then resists. There is a moment where the material beneath your thumb is denser than the material a few centimeters to the side. Not because you added anything, not because the dough changed composition, you just displaced it, concentrated it slightly, and for that moment, one region holds a little more than average, and the surrounding regions hold a little less. A density fluctuation in the early universe is something like that, except the material is not dough. The material is a plasma of quarks, gluons, photons, and a handful of other particles moving at nearly the speed of light, all at temperatures so extreme that the distinction between matter and energy was barely meaningful. And the fluctuation is not caused by a thumb, it is caused by quantum mechanics doing what quantum mechanics cannot avoid doing. Here is the part that is easy to say and surprisingly hard to actually absorb. At the scale of fundamental particles, the universe is constitutionally incapable of being perfectly smooth. This is not a failure of measurement or a limitation of instruments. The Heisenberg uncertainty principle, the same one that governs position and momentum, applies to fields of energy as well. A quantum field cannot simply sit at a fixed value everywhere all the time. It has to jitter. It has to fluctuate around its average. The fluctuations are not noise layered on top of the physics. They are the physics. So in the very early universe, across this vast, extraordinarily hot plasma, there were regions, spread across what were then tiny distances that would later be stretched enormously by cosmic expansion, where the energy density happened to be slightly above the average, not by much, a fraction of a percent above. Nearby regions were correspondingly slightly below. These deviations were not dramatic. They were not visible in any meaningful sense, because nothing could see. There was no light propagating freely, no observer, no instrument. Just the field fluctuating as it was bound to do. The key word there is inevitable. This matters more than it might seem. When something is described as a quantum fluctuation, there is a temptation to hear it as a lucky accident, as though the universe happened, by chance, to produce a wrinkle in the right place at the right time. That is not quite what happened. The fluctuations were not fortunate. They were guaranteed. Quantum mechanics does not permit the absence of fluctuations. What the universe did not guarantee was which fluctuations would be large enough in the right conditions to do something permanent. Most would not. Most would simply oscillate, rise slightly, fall slightly, disperse into the surrounding plasma without consequence, like ripples crossing each other on a pond and flattening back to nothing. But some, a small fraction distributed across what would eventually become enormous scales, were large enough specifically that when the right moment arrived, gravity could grip them. It is worth pausing on what large enough means here because it is not large in any ordinary sense. The overdensity needed to eventually seed a primordial black hole was still tiny in absolute terms, a few percent above the background perhaps. In the early plasma, that translates to a small difference in pressure, a small excess of energy in a region that was itself unimaginably small. Nothing that would register as significant if you were somehow watching from the outside. The strangeness is in the conditions, not in the fluctuation itself. The early universe was so uniformly dense that even a fractional deviation represented an enormous amount of energy crammed into a region that was, at that moment, smaller than a proton. As the universe expanded and those regions were stretched outward, that energy did not disappear. It went along for the ride. Embedded in the expanding fabric of space, these tiny wrinkles in the energy distribution grew in physical size while preserving their relative overdensity, which means the fluctuation you are trying to picture is not a lump sitting in empty space. It is a region of a continuous field that happened to be denser than its neighbours, carried outward by expansion, persisting because quantum mechanics wrote it in first and the universe had no mechanism to erase it. Whether any given fluctuation eventually became something, a galaxy, a cluster of galaxies, a primordial black hole, depended on its amplitude when it re-entered the Hubble horizon, and on what the universe was doing at that precise moment. We will get to both of those things, but for now the important point is simpler than it might seem. The fluctuations were not optional. They were not inserted into the early universe by some external process. They came with the territory. They came with quantum mechanics, which came with everything. The universe, in its first moments, could not have been born smooth. And that roughness, faint, tiny, already ancient before the first proton had fully formed, is what everything that follows is made of. Before the universe had cooled enough to form a single proton, before the quark-gluon plasma had begun to organize itself into anything with structure or mass, something happened to space itself. Not to what was inside space. To space. It excincted. And it did so at a rate that makes every other expansion in cosmic history look like a held breath. This period is called inflation, and it lasted an extraordinarily short time by any measure, something on the order of 10 to the minus 32 seconds, depending on which model you trust, and there are several worth trusting. In that interval, the observable universe grew from a region smaller than a proton to something roughly the size of a grapefruit, which sounds almost manageable until you sit with the rate. The universe did not just expand quickly, it doubled in size repeatedly, tens of times over, in less time than it takes light to cross the width of a hydrogen atom. That kind of expansion does something very specific to anything caught inside it. Go back to the fluctuations from the previous chapter, the quantum jitter in the energy field. Those tiny inevitable deviations from the average, the ones that quantum mechanics writes in automatically, that could not be smoothed away because the uncertainty principle does not permit smoothness. In an ordinary setting, fluctuations like these are transient. They appear and disappear on timescales so short they have no lasting effect. A quantum fluctuation in a field normally lives and dies within the constraints of what physicists call the Heisenberg time-energy relationship. The smaller the energy involved, the longer it can persist. But even the longest-lived ones vanish without leaving a mark. Inflation interrupted that process. When space expanded as rapidly as inflation required, fluctuation that existed on quantum scales was stretched outward before it had time to collapse back on itself. The stretching happened faster than the fluctuation could respond, faster than any signal could travel across it to coordinate a return to equilibrium. And so the fluctuation was caught mid-existence, pulled to a scale where quantum behavior no longer applied, where the rules that would normally erase it simply stopped being relevant, and deposited, imprinted is probably the better word, into the fabric of space as a classical perturbation. A real physical deviation in the energy density of the universe, now frozen at a scale billions of times larger than it had been a fraction of a second before. Think of a camera shutter closing so fast that even a moving subject appears perfectly sharp. No blur, no averaging out of the motion, just a frozen moment captured exactly as it was. Inflation did something like that to the quantum world. It took fluctuations that would ordinarily blur themselves into nothing and froze them in place, imprinted at macroscopic scales before they could disappear. The result was a universe emerging from inflation with a specific texture, not smooth, not random in the way white noise is random, flat and featureless across all scales. Instead, it had a structured roughness, a spectrum of fluctuations of different sizes and amplitudes, distributed across space in a pattern that reflected exactly what the quantum field had been doing at the moment inflation caught it. This spectrum is what cosmologists call the primordial power spectrum, and it is, in a very real sense, the universe's earliest surviving document. The CMB, the cosmic microwave background, the faint thermal afterglow detected by satellites, is essentially a photograph of this texture, taken when the universe was about 380,000 years old and first became transparent. So inflation did two things simultaneously. It solved a set of problems that the standard Big Bang model had no answer for. Why the universe looks so uniform on large scales, why it is so geometrically flat, why regions of the sky that could never have been in contact with each other still have the same temperature. And it produced, as a byproduct of solving those problems, the exact kind of structured inhomogeneity that everything else in the universe is built from. Galaxies, galaxy clusters, the cosmic web, and, if the amplitude of the fluctuations at small scales was high enough, something else. Something that formed much earlier than any of those structures in the radiation-dominated plasma that inflation left behind. Without inflation, the fluctuations would not have survived long enough to matter. They would have appeared and vanished over and over, leaving no record. The universe might have emerged from its earliest phase genuinely smooth, and a smooth universe, one where every region is identical to every other, is a universe where gravity has nothing to grip. No overdense regions to collapse, no seeds, no structure forming at any scale, no stars, no galaxies, no us in the most fundamental sense. And, this is the part that is easy to gloss over, no primordial black holes. Because primordial black holes require exactly what inflation produced. Fluctuations large enough in the right range of scales to survive the radiation era long enough to re-enter the Hubble horizon with sufficient amplitude to collapse. Inflation is not the background context for this story. It is the mechanism that made the story possible. What it left behind was a universe seeded with wrinkles of different sizes, some of which were already in the first microseconds carrying the instructions for collapse. Not all of them, not most of them, but some. The question of which ones, and what determined whether they would fall inward or disperse, is where the next part of this lives. There is a specific frustration that comes from looking at a graph where two numbers refuse to connect. Not because the graph is wrong, because it is right, and what it shows is a gap so large that the scale on the vertical axis stops feeling like a measurement and starts feeling like a commentary. That is roughly the situation with the primordial power spectrum and primordial black holes. The power spectrum is a way of describing how much structure the early universe had at different scales. Think of it as a record of how lumpy space was, how much the energy density deviated from the average, plotted against the size of the region you're measuring. Large regions on one end, small regions on the other. The height of the curve at any given point tells you the typical amplitude of fluctuations at that scale. At the scales we can actually measure. The scales probed by the cosmic microwave background, ranging from the full width of the observable universe down to roughly the size of a galaxy cluster. The spectrum is nearly flat. The deviations from average energy density are tiny, around 1 part in 100,000. Uniform enough that the CMB looks almost featureless to the naked eye, its temperature varying by less than 1/10 of a degree across the entire sky. The spectrum at these scales has been measured with extraordinary precision by satellites, and it fits a simple mathematical shape almost perfectly. Physicists describe it as nearly scale invariant, meaning the amplitude of fluctuations is roughly the same regardless of which large scale you examine. This is, in one sense, remarkable. The early universe was astonishingly smooth at the scales we can see. Now go to smaller scales, much smaller. The scales relevant to primordial black hole formation are not galaxy-sized or cluster-sized. They are tiny, corresponding to the horizon size of the universe at fractions of a second old. These are scales that left no direct imprint on the CMB, because they were already well inside the horizon by the time the CMB formed. We have no direct measurement of the power spectrum there. No satellite has seen it. No instrument has reached it. We are, at these scales, working from inference and theory. And what theory requires, if primordial black holes are to form in any meaningful number, is a power spectrum at those small scales that is not flat, not nearly flat, not slightly elevating. The amplitude of fluctuations needs to be approximately 10 million times larger than what the CMB shows at large scales. 10 million, 7 orders of magnitude. That number deserves a moment of stillness. It means that the early universe, if it produced primordial black holes, was not uniformly lumpy across all scales. It was smooth in the places we can see and violently rough in the places we cannot. The same universe, the same spectrum, but with a peak at small scales so enormous that comparing it to the CMB end of the spectrum is like comparing a faint pencil mark to a mountain range. The reason this is a problem, or a constraint, which is perhaps the more precise word, is that inflation does not automatically produce this. Standard slow-roll inflation, the simplest inflationary model, generates a nearly scale-invariant spectrum across essentially all scales, flat from the largest to the smallest. That is actually one of its virtues as a theory. But it is also, from the perspective of primordial black hole formation, a limitation. A universe with a purely flat spectrum would produce essentially no PBHS. The fluctuations at small scales would simply be too mild to collapse into anything. To get the enhancement, inflation has to behave differently at some point during its evolution. Something has to cause the inflaton field, the field driving the expansion, to slow down briefly, or encounter a feature in its potential energy landscape, or undergo some departure from the smooth, steady roll that simple models assume. Different theoretical frameworks achieve this in different ways. Ultra-slow roll inflation, where the field temporarily loses almost all its momentum. Two-stage inflation, where a second field activates partway through. Models with sharp features or dips in the inflationary potential. All of them produce a localized enhancement in the power spectrum at specific scales, a peak, rising steeply above the otherwise flat baseline. Whether any of these models correctly describes what actually happened is, well, that is not settled. The honest position is that we have multiple plausible mechanisms and no direct way, yet, to distinguish between them using existing observations. The peak in the power spectrum that primordial black holes require exists, in our models, at scales we cannot currently probe directly. We infer its presence from the existence of PBHS themselves, which we have not yet confirmed with certainty. The argument has a circular quality that physicists are aware of and uncomfortable with, in the way that physicists get uncomfortable. Quietly, precisely, and productively. What we can say is this. For primordial black holes to exist in numbers large enough to matter, large enough to account for a meaningful fraction of dark matter, or to explain any of the anomalies we will come to later, something unusual had to happen during inflation at small scales. The universe had to be far rougher there than it is anywhere we can see. Whether it was is exactly the question the field is currently trying to answer. Every point in the universe has a horizon, not a visible edge, not a wall, not a boundary you could fly toward and eventually reach. Something more fundamental than that, and in some ways stranger. It is the distance beyond which, at this particular moment in time, no signal has had enough time to travel from there to here since the universe began. Light moves at a fixed speed. The universe has a finite age. Multiply one by the other, and you get a sphere, the Hubble horizon, beyond which, for any given observer, causality simply does not extend. What lies beyond the horizon is not unreachable in principle. It is unreachable right now by definition, because information cannot travel faster than light, and the universe is not old enough for that information to have arrived yet. But the horizon is not fixed. As the universe ages, the horizon grows. More of the universe becomes causally accessible over time. Regions that were once beyond reach gradually come within reach as the light from them, finally, after billions of years, completes its journey. This expanding accessibility is what makes the horizon relevant to primordial black holes. Not the horizon itself exactly, but the moment when something crosses back inside it. Here is the sequence. During inflation, quantum fluctuations were stretched to scales far larger than the Hubble horizon of the time. They became super-horizon perturbations, wrinkles in the energy density of the universe that were physically larger than the region within which any causal process could operate. And because no signal could cross them fast enough to smooth them out, they simply sat there, preserved as the universe evolved around them. The horizon, meanwhile, was extremely small during inflation, growing, but slowly relative to the rate at which the fluctuations were being stretched outward. So nearly everything that inflation amplified ended up parked outside the horizon, waiting. After inflation ended, the dynamic shifted. The universe's expansion slowed from that extraordinary inflationary rate, the more measured expansion, of the radiation-dominated era. The horizon grew much faster now, expanding at roughly the speed of light relative to the surrounding plasma, and this is where the trap begins to close. Imagine a room. The furniture in it keeps increasing, chairs, tables, boxes piling in from every direction. The room is not shrinking, the room is the same size it always was, but the usable space inside it is collapsing, crowded out by things accumulating from the edges inward. That is roughly what it felt like, in a purely geometric sense, for a super-horizon fluctuation as the Hubble horizon expanded outward toward it. The fluctuation had been sitting safely beyond the causal boundary, untouchable, unable to interact with the universe in any dynamically meaningful way. But the horizon was growing, and eventually, depending on the physical size of the fluctuation, which depended on when during inflation it had been produced, the horizon caught up. The fluctuation crossed back inside. It re-entered. This moment of horizon re-entry is the only window in which collapse is possible. Before re-entry, the fluctuation is causally inert. It exists, it has an amplitude, it carries an excess of energy density relative to its surroundings, but nothing can act on it. No gravitational process can organize itself across scales larger than the horizon. After re-entry, the fluctuation is suddenly inside a region where causal physics can operate. Gravity can reach across it. Pressure can respond to it. The surrounding plasma can feel it. What happens next depends on the amplitude of the fluctuation, on how much denser it is than the background plasma at the moment of re-entry. This is the threshold question, and we will come to it in the next chapter. But the spatial picture is worth holding on to before moving forward. The trap is not built by gravity alone. It is built by the geometry of causality. An overdense region that spent the entirety of the inflationary and early radiation eras safely parked outside the horizon, untouched, uncompressed, simply carried outward by expansion, suddenly finds itself inside a universe that can feel it. The horizon closes around it not like a fist, but like a slowly rising tide. And once it is inside, once the horizon has grown past it, the overdense region is no longer protected by causal disconnection. It is exposed. Whether gravity wins from that point is not guaranteed. Most fluctuations, even on re-entry, are not dense enough. The radiation pressure in the early universe was formidable, and it does not give way easily. Most overdense regions re-enter the horizon and simply begin to oscillate, compressing, rebounding, compressing again, sending acoustic waves through the plasma and eventually dispersing into it. The energy goes somewhere, just not downward. But some, and here is where the hesitation belongs because the numbers are genuinely small, some arrive at the horizon boundary with enough amplitude that the outcome is not oscillation. The overdense region is dense enough and compact enough, and the gravitational self-energy is large enough that the inward pull overwhelms the outward pressure before the region has time to rebound. In those cases, the trap closes completely. What began as a quantum fluctuation stretched by inflation, frozen in place, carried across billions of times its original scale, re-entering the horizon in a plasma of unimaginable temperature, collapses, not slowly, not gradually, in a fraction of a second. And whatever was inside the horizon at that moment, all of that energy, all of that mass, becomes unreachable, permanently. A primordial black hole formed from pure radiation in the first moments of the universe's life. The horizon built the trap, gravity pulled it shut. Press your palm flat against a wall that is vibrating, not shaking violently, just humming quietly with something moving on the other side. You feel the push before you understand it. The resistance is impersonal. It does not care about your hand. It is simply what pressure does. It pushes outward in all directions, with total indifference to what is in the way. The radiation-dominated early universe had that quality. The plasma filling all of space was under pressure so enormous that the number attached to it becomes meaningless without context. Every cubic centimetre of that plasma contained photons, quarks, and other relativistic particles moving at or near the speed of light, constantly colliding, transferring momentum in every direction simultaneously. The pressure was not a secondary property of this material. It was half of what the material was. In the language of physics, the radiation equation of state means that pressure equals 1/3 of energy density. You cannot have the energy without the pressure. They come together. This is what an overdense region was entering when it re-entered the Hubble horizon. The region had excess mass, excess energy density to be precise, relative to its surroundings. Gravity, which responds to energy density in a relativistic plasma just as it responds to mass in ordinary matter, immediately began pulling the region inward, trying to concentrate it further, trying to collapse it. But the plasma inside the overdense region was under the same radiation pressure as everything else. As gravity compressed the region, the pressure increased. As the pressure increased, it pushed back. The region was caught between these two tendencies, inward gravitational pull and outward radiation resistance, and which one won depended entirely on the amplitude of the density contrast at the moment of horizon entry. How much denser was this region really, compared to the background? For the overwhelming majority of fluctuations, the answer was not dense enough. The gravitational pull was real, but the radiation pressure was stronger. As gravity tried to compress the region, the pressure built faster than gravity could overcome it. The region compressed to a peak, then rebounded. The excess energy did not collapse. It radiated outward as a pressure wave, an acoustic wave, a sound wave in the most literal physical sense, propagating through the plasma at roughly 60% of the speed of light. These acoustic waves are not a side note, they are the dominant outcome. They are what happened to almost every fluctuation that ever re-entered the horizon in the radiation era. The energy went into the wave propagated outward, crossed other waves, interfered with them constructively and destructively, and eventually, hundreds of thousands of years later, when the universe cooled enough for atoms to form, left their imprint in the temperature fluctuations of the cosmic microwave background. The small hot and cold spots in the CMB are, in a very real sense, the fossil record of all the overdense regions that tried to collapse and didn't. The waves they made, frozen in the last moment the universe was still a plasma. So when you look at the CMB, you are looking at the graveyard of collapse attempts. All those fluctuations that re-entered the horizon felt gravity pulling inward and lost. Not violently, not catastrophically. They lost quietly, bouncing back, sending their energy into waves that crossed the universe for 380,000 years before leaving a faint temperature pattern that satellites can now measure. Gravity, in those cases, was real. It was not weak. It was simply outmatched. The collapse cases were different in one specific way. Not in kind, the same two forces were competing. Different only in the initial amplitude. A fluctuation that crossed the horizon with a density contrast above a certain threshold, a number we will pin down more precisely in the next chapter, but roughly a few tens of % above the background, entered a regime where gravity's accumulating advantage could outrun the pressure response before the pressure had time to fully mobilize. The key is the time scale. Pressure is fast, but not instantaneous. Information about the pressure state of one part of the region has to travel to other parts before the region can respond coherently. That information travels at the sound speed of the plasma, which is high but finite. For a sufficiently large overdensity, gravity can pull the region inward faster than the pressure response can propagate across it. The outer edges have not yet received the signal that says compress outward. And by the time they would have, the interior has already crossed a point of no return. This is, I want to be careful here, because it is easy to overdramatize. This is not an explosion, not a dramatic event visible in any conventional sense. What happens is that the inward motion accelerates. The region shrinks, the density rises. The density rising makes gravity stronger. Stronger gravity accelerates the inward motion further. And this feedback loop, once it begins, does not reverse. There is no rebound. There is no acoustic wave carrying the energy safely away. The energy stays where it is, inside a region that is getting smaller and denser, until the mathematics of general relativity take over completely. What forms is a black hole? One that has never been anything else, never a star, never a gas cloud, never a galaxy nucleus. It was a quantum fluctuation, then a classical perturbation, then a collapsing over dense region in a radiation plasma, and then a black hole, in a process that took a fraction of a second from horizon entry to completion. And this happened how often? Not often. The physics does not permit it to be common. The threshold amplitude required for collapse means that only the extreme tail of the fluctuation distribution, the rarest of the rare, the overdense regions that were far outside the typical range, could achieve it. The vast majority bounced. The vast majority became acoustic waves. The vast majority became the temperature spots in the CMB. Each primordial black hole represents a fluctuation that was exceptional by every statistical measure. A local temporary total victory of gravity over a force that won almost everywhere else. Almost everywhere. Not everywhere. There is a number at the centre of this story. Not the only number, but the one everything else pivots around. It is called the critical density contrast, written in the physics literature as delta sub c. And it represents the minimum excess density a fluctuation must carry at the moment of horizon re-entry in order to collapse into a black hole rather than disperse. The number is not large. That is the first thing worth saying about it. A density contrast of, say, 0.5 means the region is 50% denser than the surrounding plasma. In everyday terms, that sounds substantial. In the context of the early universe, where you are trying to overcome radiation pressure that fills all of space with nearly uniform intensity, it is the minimum purchase gravity needs. Not much, just enough. Bernard Carr worked out the first analytic estimate of this threshold in 1975, building on the framework he and Hawking had established the year before. His approach was elegant but necessarily approximate. He was working with simplified models of the collapse dynamics, assuming spherical symmetry and a clean radiation equation of state, and extracting from those assumptions a rough value for when the gravitational self-energy of an overdense region would exceed the pressure forces resisting it. The number he arrived at was around 1/3. Specifically, delta sub c is approximately 1/3, which is the same value as the ratio of pressure to energy density in a radiation-dominated fluid. A kind of dimensional inevitability. When the overdensity exceeded the equation of state parameter, gravity would win. It was a good estimate, useful for 2 decades of theoretical work. But it was wrong in detail, and later physicists knew it. The problem was that the analytic approach could not capture the full nonlinear dynamics of what actually happens during collapse. As a region approaches its threshold, the behavior becomes genuinely complex, pressure waves competing with infall. The geometry of the surrounding space-time curving in ways that affect the dynamics, the shape of the overdense region mattering in ways a spherical approximation cannot fully account for. To get the threshold right, you needed numerical simulations. Specifically, you needed numerical simulations using the full machinery of general relativity. Those simulations came in the late 1990s from Niemeyer and Adamczyk, and they shifted the number upward considerably. When they defined the density contrast as the total excess mass within the initial horizon volume, which turns out to be the physically cleaner definition, the threshold came out near delta sub C, approximately 0.7, not 1/3, not close to 1/3, more than twice the original estimate. More recent work using three-dimensional general relativistic codes has refined this further, producing values in the range of 0.4 to 0.7, depending on the exact definition used and the shape of the perturbation profile being simulated. Different initial conditions, different profiles, slightly different thresholds. The number is not a single clean value, it is a range, and the range reflects genuine physical variability in how collapse can proceed. What the simulations confirmed, and what the analytic work had only implied, is what crossing this threshold actually looks like in practice. It is not gradual, that is the part that is easy to understate. Below the threshold, an overence region compresses, peaks, and rebounds, the whole cycle playing out over a sound crossing time, the time it takes a pressure wave to traverse the region. That timescale, at horizon re-entry in the early universe, is extremely short, but the region does go through a full cycle. There is compression, and then there is release. Above the threshold, there is no release. The infall begins and the pressure response cannot catch up. The region does not oscillate. It does not pause at peak compression and consider its options. Gravity is already ahead of the pressure gradient by the time the pressure gradient forms, and it stays ahead. The infall accelerates. The density rises. The density rising makes the gravitational field stronger. The stronger gravitational field accelerates the infall further. Think of a lock turning, not a slamming door, something quieter than that. A mechanism engaging, a small definitive click, and then the door is simply closed. The moment the density contrast crosses delta sub C, the outcome is settled. Not immediately apparent from the outside, perhaps, because the collapse still takes a fraction of a second to complete, but settled. The way a stone thrown past the lip of a cliff is settled before it begins to fall. The decision was made at the threshold. Everything after is a consequence. Within a fraction of a second and fractions of a second so small they have no intuitive equivalent, the region has collapsed past the point where general relativity permits any other outcome. An event horizon forms. Whatever was inside the Hubble horizon at the moment of re-entry, whatever energy density was contained in that volume of plasma, is now enclosed. Permanently. The black hole does not announce itself. Nothing outside its event horizon changes in any dramatic way. The surrounding plasma continues expanding, cooling, evolving. The QCD transition will happen. Protons will form, eventually atoms will form, then stars. The universe will grow enormously in complexity over the next 13 billion years. The black hole will simply be there, still, unchanging in most of the ways that matter. Carrying the mass it was born with or close to it depending on its size and what Hawking radiation does to it over time, it formed from the threshold, from a number, from a density contrast that happened to be in the tail of a distribution, in the right place at the right moment, and it will not unform. Most things acquire their mass gradually. A star spends millions of years pulling gas inward, compressing it, fusing it, building mass through accumulation and process. A planet gathers dust and rock over millions of years of orbital sweeping. Even a stellar black hole, which forms quickly in cosmic terms, inherits its mass from a star that spent its entire life building up to that moment. There is a history to the mass, a biography. Primordial black holes have no biography, they have a timestamp. The mass of a primordial black hole is determined almost entirely by a single variable, the moment in the universe's history when it formed, not the composition of the plasma that collapsed, not the temperature of the surrounding material except insofar as temperature maps directly onto time, not the size of the original quantum fluctuation in any independent sense, The fluctuation had to be above the collapse threshold, yes, that much we covered, but once it crossed that threshold, what determined how massive the resulting black hole would be was almost purely when the threshold crossing happened. What time it was in the universe's early life. The reason is geometric. A primordial black hole forms from the material inside the Hubble horizon at the moment of collapse. The horizon defines the available volume. The energy density of the plasma, which was extremely high early on and falling rapidly as the universe expanded and cooled, determines how much mass that volume contained. Multiply the density by the volume enclosed within the horizon radius, and you have, to a good approximation, the mass of the black hole. Both of those quantities, the horizon volume and the energy density, are functions of time, and they evolve in opposite directions. As time increases, the horizon grows, enclosing more volume. But as time increases, the energy density also falls, because the universe is expanding and cooling. The product of these two quantities is itself a function of time, and in a radiation-dominated universe it takes a specific form. The horizon mass scales as approximately 10 to the 15th grams, multiplied by the ratio of the formation time to 10 to the minus 23 seconds. Hold a coin in a closed fist and think about what 1200 billion grams actually means. Then think about what it means compressed into a black hole. The object weighs more than a small mountain and fits inside a volume smaller than a proton. A primordial black hole forming at 10 to the minus 23 seconds carries roughly that mass. 10 to the 12 grams, around 1 trillion grams, or about the mass of a small asteroid, packed into an event horizon with a radius of roughly 10 to the minus 13 centimeters, far smaller than an atomic nucleus. That is one end of the scale. At the other end, a black hole forming near 1 second after the Big Bang. By that point, the horizon has grown enormously, enclosing a region of space containing roughly 100,000 solar masses of energy. A PBH forming at that moment, if the conditions were right, if the fluctuation amplitude was sufficient, would carry that entire mass within its event horizon at birth. 100,000 times the mass of the Sun, formed not from stellar death, not from galactic dynamics, but from a density fluctuation in a plasma of quarks and photons and gluons in the first second of existence. Between those two extremes, the entire range is available. A PBH forming at 10 to the minus 5 seconds, around the time of the QCD phase transition, which we will spend time with shortly, carries a mass near 1 or 2 solar masses. Solar mass black holes formed before the first proton had finished binding, before any atom existed anywhere in the universe. The mass is written by the timing, and the timing is written by the physics of the phase transition. This is genuinely strange. I want to say that plainly rather than gloss over it. With stellar black holes, you can in principle trace the mass back through the evolution of the progenitor star, its initial mass, its composition, its position in a binary system, its rate of mass loss over millions of years. The mass has causes that stretch back through time. With a primordial black hole, the mass has essentially one cause, and it is a clock reading. The universe was this old, the horizon was this large, the density was this high, and so the mass is this number. The object carries that number forever, or very nearly forever, as an imprint of the exact moment when the trap closed. There is something almost bureaucratic about it, if you approach it from the right angle. Each primordial black hole issued, at the moment of formation, with a birth certificate stamped with a single figure. Not a name, not a composition, not a history, just a mass, derived from a timestamp, in a universe that was still almost entirely made of radiation. That number is not just a label. It determines almost everything about the object's future. The mass determines the Hawking temperature, which determines how quickly the object radiates, which determines its lifespan. A black hole with a mass of around 5 times 10 to the 14 grams has a lifespan roughly equal to the current age of the universe. Objects lighter than that have already evaporated. Objects heavier are still here, and will remain so for timescales that make the current age of the universe feel like a warm-up. All of that, the entire trajectory of the object's existence, from formation to eventual evaporation or permanent survival, is encoded in a single number. A number written not by what the object is made of, but by when it was born. The universe set the mass. It did not ask permission. And once it was written, it was not revised. 10 microseconds. That is where this chapter lives. Not 10 seconds, not 10 milliseconds. 10 microseconds after the Big Bang, 100,000th of a second into the universe's existence, when something happened to the fundamental material of the cosmos that left a mark on the black hole population that we may still be detecting today. To understand what happened, you need to know what the universe was made of at that moment. The quark-gluon plasma that filled all of space in the first microseconds was not yet organized into anything recognizable. Quarks, the constituents of protons and neutrons, were moving freely through the plasma. Gluons, the particles that ordinarily bind quarks together inside a proton, were also loose, part of the general churning hot fluid. The strong nuclear force, which under ordinary conditions locks quarks into tight triplets, was present and active, but at high enough temperatures, the thermal energy of the plasma is simply too great for confinement to hold. The quarks are too energetic to be bound. They move freely, as if the strong force were barely there. As the universe expanded, it cooled. That is always the direction. Expansion means cooling, a thermodynamic inevitability that runs through all of cosmic history. And at around 10 microseconds, the temperature dropped to a value that physicists call the QCD confinement scale, roughly 200 mega-electron volts, or about 2 trillion degrees Kelvin. At this temperature, something changed. The quarks for the first time became bound. Free quarks and free gluons organized themselves into hadrons, protons, neutrons, pions, and a brief violent population of other short-lived particles. The quark-gluon plasma became hadronic matter. The universe underwent what physicists call the QCD phase transition, or the quark-hadron transition. This transition was not instantaneous in the way a light switch flips. It was a process that played out over some interval of time as the temperature crossed the confinement threshold. And during that interval, the behavior of the plasma changed in a way that had direct consequences for any overdense region trying to decide whether to collapse or disperse. Think of a material that is ordinarily stiff. A wax crayon left in a drawer all winter. Rigid, resistant, not yielding to light pressure. Now put it on a warm surface for a few minutes. It softens. Not melting, not liquid, but pliable in a way it was not before. The same pressure that left no impression on the cold wax now produces a dent. The material's resistance has temporarily dropped. The equation of state of the early universe behaved something like that during the QCD transition. Under normal radiation-dominated conditions, the relationship between pressure and energy density is fixed at 1/3. Pressure equals 1/3 of energy density, rigid and invariant. This ratio sets the stiffness of the cosmic fluid, its resistance to compression. The higher the ratio, the harder it is for gravity to compress an overdense region faster than pressure can push back. During the QCD transition, this ratio dipped. Not dramatically. The softening was around 10% in terms of the collapse threshold. The critical density contrast delta to sub-C dropped by roughly that amount, which sounds modest. 10% is not a large change in everyday terms. But the formation rate of primordial black holes is not a linear function of the threshold. It is exponential. Because the fluctuation distribution in the early universe was Gaussian, the probability of a fluctuation having a given amplitude fell off exponentially as the amplitude increased. Even a small reduction in the threshold opened the distribution to a vastly larger number of qualifying fluctuations. Fluctuations that were previously just below the threshold, that would have dispersed as acoustic waves under normal conditions, now found themselves above it. The gap between their amplitude and the collapse requirement had closed. By the way, I forgot to mention something earlier. On Patreon there are over 50 episodes, audio biographies of scientists both famous and nearly forgotten by history, and a lot of content that goes deep into topics this channel loves. If any of that sounds interesting, the Patreon link is in the description. The result, confirmed by detailed numerical simulations, was a 1,000-fold increase in PBH formation at the mass scales corresponding to the QCD transition. A factor of 1,000, not 10, not 50, 1,000 times more black holes forming in that brief window than would have formed in an equivalent period of purely radiation-dominated expansion without the transition. And the mass scale corresponding to the QCD transition is solar mass. The horizon at 10 microseconds encloses roughly 1 to 2 solar masses of energy, which means the black holes that form during the QCD pause, if they formed at all, which the physics strongly suggests they did, formed with masses near those of stellar black holes, near the masses of the objects that LIGO and Virgo detect when binary black holes merge. This is not a coincidence that the field ignores. The QCD transition is the reason solar mass primordial black holes are theoretically favoured over most other mass scales. The universe briefly lowered the barrier at exactly the mass scale where our gravitational wave detectors are sensitive. Whether that alignment means something detectable is one of the open questions sitting at the edge of current research. What the transition was, physically, was a pause. A brief interval in which the plasma's resistance to collapse softened, gravity found a narrower gap than usual, and an extraordinary number of overdense regions crossed into territory from which there was no return. The pause lasted only a fraction of the 10 microseconds that framed it. The hadronic phase established itself. The equation of state stiffened back toward its radiation value, and the window closed. The universe resumed its normal resistance. The acoustic waves began bouncing again, and the majority of fluctuations went back to dispersing harmlessly. But the black holes that formed during the pause did not disperse. They were already closed, already committed, already carrying a mass the universe had written at the moment the gap opened. 10 microseconds, one brief softening, 1,000-fold difference in what survived. 1 second after the Big Bang, the universe has already passed through its most violent infancy. The QCD transition is behind it. Protons and neutrons have formed. The temperature has fallen to around 5 billion degrees Kelvin, which is still extraordinary, but is also, in cosmic terms, a kind of settling. The plasma is becoming something recognizable, at least in outline. The ingredients of future atoms are present if not yet assembled. And woven through all of it in equal measure with the matter is antimatter. Every electron in the early plasma has a corresponding positron, its antiparticle twin, identical in a mass and opposite in charge. Every proton has an antiproton. The matter and antimatter are not separated, not confined to different regions. They occupy the same space, moving through the same plasma, annihilating and being created again continuously in a kind of dynamic equilibrium that the temperature sustains. As long as the plasma is hot enough, the thermal energy keeps producing new particle-antiparticle pairs to replace the ones that annihilate. The balance holds. Then the temperature drops below the threshold needed to produce new electron-positron pairs. This threshold is around 1 billion degrees Kelvin, and the universe passes through it at roughly 1 second. Below this temperature, pair production stops. Electrons and positrons can still find each other and annihilate, converting their combined mass into photons, but no new pairs are being created to replace them. The positrons begin to disappear. Not instantly. The process takes some time, fractions of a second, in a universe whose dynamics are still moving quickly. But the direction is one way. The positrons thin out. The annihilation events continue, each one releasing 2 photons and reducing the positron population by 1. The sound of it, if you tried to render it in some abstract way, would be less like an explosion and more like something fading, a frequency slowly dropping out of a room's ambient noise, not stopped but thinned, until it is no longer there. What was left was a small excess of electrons over positrons, the asymmetry that had always existed but had been obscured by the overwhelming number of pairs. That asymmetry is the matter we are all made of. the positrons that vanished at 1 second, they were, in a sense, the majority. What survived was the remainder. But the vanishing did something else. It changed the equation of state. The Electron-Positron Annihilation Epoch reduced the number of relativistic particle species in the plasma. When positrons disappeared, the energy they carried was absorbed into the photon bath, reheating it slightly. The effective number of degrees of freedom, the parameter physicists use to count how many species are contributing to the plasma's pressure and energy density, dropped. And when that parameter drops, the relationship between pressure and energy density shifts. Not by much, not as dramatically as during the QCD transition, but enough. The equation of state softened again. The resistance of the cosmic fluid to gravitational collapse dipped for the second time since the Big Bang, and the mass scale corresponding to the horizon at 1 second is, again in the solar mass range, somewhat higher than the QCD peak, but overlapping with it, contributing a second enhancement to the PBH formation rate in a mass window that had already been favoured. The enhancement during electron-positron annihilation is smaller than the QCD one. The softening is less pronounced, the threshold reduction less severe, but it is real, and it is calculable, and it contributes a distinct feature to the PBH mass function. A secondary bump at masses somewhat above the QCD peak, in the range of a few solar masses that models of the early universe predict with reasonable confidence. And here is the thing that is, genuinely, difficult to hold without letting it slip away. Some of the black holes that LIGO has detected, the ones with masses between 1 and a few solar masses, the ones that do not fit comfortably into standard stellar evolution models, may have formed at this moment, at 1 second after the Big Bang, in the instant when the positrons were finishing their disappearance from the universe and the plasma was briefly softer than it had any right to be. The merger events that LIGO records today, the gravitational waves that travel billions of years to reach detectors buried in Louisiana and Washington state, they may be echoes of a collision between two objects born 1 second into the universe's existence, born from antimatter's departure, born from a window that lasted a fraction of a breath and then closed forever. Whether that is true is not settled. The signal exists. The mechanism is physically sound. The timing is right. What is missing is confirmation that no other explanation fits the observations as well. 1 second. The positron's gone, something left behind in the softness. The oldest stars in the observable universe are somewhere between 13 and 13.5 billion years old. They formed in the first few 100 million years after the Big Bang from hydrogen and helium gas that had cooled enough to collapse under gravity into clouds, then into cores, then into the first nuclear furnaces. Population 3 stars, the designation physicists give them, massive, hot, short-lived, burning through their fuel in a few million years before exploding or collapsing. They were the first generation. Nothing came before them in terms of stars, but something came before them, something that had already been sitting in the universe for hundreds of millions of years by the time the first Population 3 star ignited. Primordial black holes formed in the first second after the Big Bang. Some formed in the first microsecond, some at 10 to the minus 23 seconds, a timescale so removed from human experience that the word early does not cover it. These objects were already old in their way, before a single hydrogen atom had bonded to another, before the cosmic microwave background had formed, before nucleosynthesis had produced the first helium nucleus. They sat in the expanding plasma as it cooled around them, unchanged in any fundamental way, while the universe underwent every transformation it would need to undergo before a star was possible. Hold a smooth river stone in your hand sometime. It has a weight and a texture that feel completely ordinary. The kind of object you pick up without thinking. But the stone might be 400 million years old. The riverbed shaped it. The glaciers moved it. Continental plates shifted beneath it. And it carries none of that on its surface. It just feels like a stone. The age is not in the texture. It is in the history which the object does not announce. Primordial black holes are like that, except the timescale is not for 100 million years, but 13 billion, and the history is not geological but cosmological, and the object is not a stone but a gravitational singularity surrounded by an event horizon that has never, in all that time, permitted a single thing to leave. Every other black hole in the universe has a story that begins with a star. Stellar mass black holes form from the core collapse of massive stars, objects that have to live for at least several million years before they are heavy enough and evolved enough to produce a black hole when they die. Supermassive black holes at the centers of galaxies form through a combination of accretion and mergers over billions of years, their histories tangled up with the histories of the galaxies they inhabit. Intermediate mass black holes, the category between stellar and supermassive, are still poorly understood but almost certainly involve stellar processes of some kind. Every category requires stars. Every category requires time, millions of years at the absolute minimum, billions of years in the typical case. PBHs required neither. They formed from a plasma of quarks and photons and gluons before any atom existed, before any molecule existed, before any chemistry of any kind was possible. The universe at the moment of their formation was not yet a place where complexity could exist. It was a hot, dense, nearly uniform fluid, and in that fluid certain regions, rare regions, statistically exceptional, collapsed inward before the surrounding material had any opportunity to organize itself into something more structured. The word black hole is doing a lot of work here, and I am not sure it's quite equal to the task. We use the same term for an object formed from a dying star after billions of years of stellar evolution, and for an object that condensed from a primordial plasma in the universe's first second, an object that has never been anything other than what it is right now. The same mathematics describes both, the same event horizon, the same gravitational effects, the same behavior observed from the outside. But the origin is so categorically different that it is almost a different kind of thing, wearing the same name by coincidence of mathematics rather than by genuine kinship. A stellar black hole is the end of something, the terminal stage of a long process. It inherits its mass, its spin, its charge from everything that came before it, from the star's formation, its fusion history, its mass loss, its final collapse. It is, in that sense, a product of the universe's later complexity. A primordial black hole is not the end of anything, it is a remnant of the beginning. It did not inherit its properties from a prior life. It received them directly and completely from the conditions of the early universe at a single moment in time. It formed in a plasma and has sat inside an expanding universe ever since, growing older as the universe grew older, but not evolving the way stars and galaxies and even other black holes evolve. Just present, just there, older than the first atom, older than the first nucleus, older than the first star by hundreds of millions of years, at minimum. Formed when the universe was still a kind of pure energy, before it had decided what it was going to be. That is not an exotic variant of a familiar object. It is something genuinely different, described by a familiar mathematics, sitting quietly inside a universe that built everything else around it long after it had already arrived. Whether any of them are still here, whether they survived long enough to be present in the universe we inhabit now, depends on a number, the mass they were born with. And what time does to mass? That is what the next chapter holds. There is a certain kind of question that physicists describe as annoying in the most productive sense. Not annoying because it is trivial. Annoying because it sits there, seemingly simple, resisting every attempt to answer it cleanly, hinting that the resistance is telling you something important about the framework you are using rather than about the question itself. For Stephen Hawking in the early 1970s, that question was this: what happens to a very small black hole over time? He had been thinking about primordial black holes for several years by then. He and Carr had established that they could form in the radiation-dominated early universe. They had shown the accretion problem that Zeldovich and Novikov had worried about was not fatal. PBHs were viable, at least theoretically, and Hawking characteristically had pushed further. If these objects formed with masses near the Planck scale, if the smallest possible PBHS were genuinely tiny, then what would they do? How would they behave over the age of the universe? Would they just sit there? General relativity, unmodified, gives a clean answer. A black hole does nothing over time from the outside. It has a mass, a spin, a charge, and an event horizon, and it maintains all of those properties indefinitely unless it accretes matter, or merges with something. It does not shrink. It does not radiate. It does not decay. The classical theory is silent on the question of what happens to a small black hole left alone for a long time, because the classical theory says nothing happens. But Hawking was not satisfied with that. The question kept pulling at him, or so the history suggests, though the interior of another person's thinking is not something anyone can access with confidence. What he suspected was that the classical answer was incomplete, that quantum mechanics, which general relativity ignores at the level of individual particles near the horizon, had something to say. What quantum mechanics says about empty space is that it's not empty. The vacuum, the lowest energy state of a quantum field, is not a passive, featureless background. It is alive with fluctuations. Virtual particle-antiparticle pairs appear and annihilate continuously everywhere on timescales too short for any instrument to resolve. These are not real particles in the sense of being detectable under ordinary circumstances. They borrow energy from the vacuum, exist briefly, and return it. The vacuum accounts for them statistically and remains at its ground state. Near an event horizon, something changes about this process. The gravitational field at the horizon is intense enough, and, for a small black hole, the curvature of space-time extreme enough that the virtual pairs near the horizon are pulled apart before they can annihilate. One partner falls inward, crossing the horizon, becoming absorbed into the black hole. The other escapes outward. From outside the black hole, this escaping partner looks exactly like a real particle, emitted by the black hole carrying real energy. The black hole loses the energy required to promote the virtual particle to a real one. Its mass decreases. Pull one thread and something larger comes with it. Hawking pulled the thread of what happens to small PBHs, and what came with it was the realization that black holes radiate, that they have a temperature, that they are thermodynamic objects in a sense nobody had considered before, that every black hole, regardless of how it formed, regardless of its mass, must be slowly losing energy to the quantum vacuum around it, at a rate inversely proportional to its mass. The result, published in 1974, changed theoretical physics in ways that are still not fully resolved. It introduced a direct conflict between quantum mechanics and general relativity at the level of information. The information paradox, the question of what happens to the information about everything that fell into a black hole when the black hole finally evaporates completely. That problem remains open. It has generated more papers than almost any other question in theoretical physics over the past 50 years. All of it traces back to a question about primordial black holes, not abstractly, specifically. Hawking was trying to understand what tiny PBHS would do over time. The answer required him to apply quantum field theory and curved space-time, a combination that nobody had fully worked through in that context before. And the answer was not just that small PBHS would evaporate. The answer was that all black holes evaporate. That evaporation is a fundamental property of event horizons, independent of how the black hole formed or what is inside it. I find this genuinely strange to sit with. This is a case where a speculative idea about objects that had never been observed and whose existence remained entirely theoretical generated the most important result in black hole physics, not through direct experiment, not through observation, through the sustained discomfort of a question that did not have a satisfying answer within the existing framework. If PBHs had been dismissed entirely after Zeldovich and Novikov's initial skepticism, if no one had taken seriously the possibility that black holes could form in the first second of the universe, there is no guarantee Hawking would have been led to the same question through a different path. He might have. Physics often arrives at the same destination through multiple routes. But there is no certainty of that. The discovery might have come later. It might have come from someone else, through a different motivating problem, at a different time. It came from Hawking in 1974 because he was following primordial black holes down a thread that turned out to reach much further than the question he started with. The objects he was trying to understand are still unconfirmed. The result they led him to is still unconfirmed by direct observation. Both remain theoretical, both remain deeply important, and both emerged from the same moment of productive annoyance with a question that general relativity alone could not answer. The temperature of a black hole runs backward from what you might expect. Larger objects are colder, smaller objects are hotter. A black hole, the mass of the Sun, has a Hawking temperature so close to absolute zero that it is effectively undetectable against the 2.7 degree cosmic microwave background that fills all of space. It radiates, technically, but at a rate so negligible that the word evaporation feels like an insult to the timescale involved. The Sun mass black hole would take roughly 2 times 10 to the 67 years to evaporate completely, a number so far beyond the current age of the universe that the comparison becomes almost meaningless. Now make the black hole lighter, 100 times lighter, 1,000 times lighter. The temperature rises, the radiation intensifies, the evaporation accelerates, and the lifetime shrinks, not linearly but as the cube of the mass. Halve the mass, and the lifetime drops by a factor of 8. Reduce the mass by a factor of 10, and the lifetime drops by a factor of 1,000. The relationship between mass and lifespan is steep and unforgiving, and it means that across the mass range of primordial black holes, which spans many orders of magnitude, the corresponding range of lifetimes spans an almost incomprehensible spread, from fractions of a second to durations longer than the age of the universe by factors that have no intuitive equivalent. A candle burns faster as it shortens, not because the wax is different near the base, but because the geometry of what is left changes the dynamics of combustion. A black hole evaporating via Hawking radiation does something similar. As its mass decreases, its temperature rises, it radiates more intensely, its mass decreases faster, its temperature rises further. The process does not slow toward the end, it accelerates. The final moments of a black hole's evaporation are its hottest, most energetic, most violent. An object that spent billions of years radiating gently ends in a burst. The arithmetic of all this produces a specific critical mass. A primordial black hole that formed in the early universe with an initial mass of approximately 5 times 10 to the 14 grams, roughly the mass of a small mountain, in a volume far smaller than an atomic nucleus, has a Hawking evaporation lifetime of approximately 13 to 14 billion years, the current age of the universe, which means that PBHS, formed with this mass at the beginning of the universe, should right now be completing their evaporation. Right now is not a precise statement in cosmology, where timescales blur across billions of years, but it is not entirely imprecise either. Objects in this mass range, if they exist, are in their final stages. Their Hawking temperatures have risen to the hundreds of mega electron volts. They are radiating through high-energy gamma rays, electrons, positrons, and a cascade of other particles produced as the temperature climbs through the mass thresholds of various particle species. The final burst, the last fraction of a second of evaporation, releases energy comparable to a nuclear detonation, concentrated in a tiny volume over an interval so short it would appear to instruments as a flash. Gamma-ray telescopes have searched for these flashes. Nothing confirmed has been found. Either the critical mass PBHS do not exist in our vicinity, or they are rarer than the instruments can yet detect, or something about the evaporation picture in its final stages differs from the standard Hawking calculation in ways that change the observable signal. All three remain possible. The search continues. Below the critical mass, PBHS lighter than about 5 times 10 to the 14 grams, the arithmetic is simpler and more final. These objects formed in the early universe with lifetimes shorter than its current age. They have already evaporated, completely. Whatever they were, whatever role they played in the early universe, whatever gravitational effects they produced, they are gone. not in some distant future sense, gone already. Their evaporation completed sometime in the past, releasing their energy into the cosmos and leaving nothing behind. No remnant under the standard picture, no residue, just the thermal radiation they produced over their brief lives, long since dispersed and cooled into the general photon background. Whether that is the complete story is actually, this is where the standard picture starts to develop some tension, not entirely settled. The question of what happens at the very end of evaporation, when the mass approaches the Planck scale and quantum gravity effects become unavoidable, is genuinely open. Some theoretical frameworks predict a stable remnant, others predict complete evaporation. The information paradox, which Hawking radiation introduced, makes the question of what survives at the end of evaporation deeply consequential in ways that go beyond PBHS specifically. We will come back to something adjacent to this when we reach the memory burden effect. Above the critical mass, the picture shifts entirely. A PBH that formed with a mass of 10 to the 15 grams has a remaining lifetime many times the current age of the universe. It is still in the early stages of its evaporation by any reasonable accounting. Its Hawking temperature is slightly above the CMB temperature, meaning it is radiating at a rate only marginally above what it is absorbing from the cosmic background. It will be here, essentially unchanged, long after every star currently burning in the universe has exhausted its fuel and gone cold, and above that, objects in the asteroid mass range, the solar mass range, the ranges produced by the QCD transition and the Electron-Positron Epoch, the lifetimes extend to timescales that language genuinely struggles with. 10 to the 60 years, 10 to the 80 years. Numbers that exceed the proton decay timescale, that exceed the timescale for the quantum tunneling evaporation of stellar remnants. These objects, if they exist, are effectively permanent on any scale of time that has physical meaning for us. Somewhere in the sky above wherever you are lying right now, if the models are correct, there are primordial black holes completing their evaporation at this precise moment in cosmic history, flaring briefly, releasing a last pulse of high-energy radiation and going dark, not with any drama visible to us, not in a way that alters anything in the night, just a small ancient thing finally finishing what the early universe started. Dark matter makes up roughly 27% of the energy content of the universe. It does not emit light. It does not absorb light. It interacts gravitationally, which is how we know it is there, through the rotation curves of galaxies, the bending of light around galaxy clusters, the large-scale structure of the cosmic web, the acoustic peaks in the CMB. The evidence for its existence is overwhelming and comes from multiple independent directions simultaneously. What it actually is remains unknown. Primordial black holes have been a candidate since 1975, when Chaplin first proposed it, and the proposal has spent the intervening decades being tested against every observation that could constrain it. The process of testing has not been kind to most of the mass range. Region by region, mass window by mass window, the space where PBHS could constitute all of the dark matter has been compressed. What remains is small but real. The constraints come from several different directions, each targeting a different part of the mass spectrum through a different physical mechanism. At the low mass end, Hawking evaporation is itself a constraint. PBHs lighter than roughly 10 to the 15 grams have already evaporated, as the previous chapter established. But the evaporation of PBHs in the range just above that, 10 to the 15 to 10 to the 17 grams, produces gamma rays, electrons, positrons, and antiprotons in quantities that should be detectable against the observed cosmic ray and gamma ray backgrounds. The fact that no such excess has been definitively confirmed places an upper limit on how many PBHs in that range can exist. If PBHs in that mass range constituted all of the dark matter, the gamma ray sky would look different from what instruments observe. It does not, so they cannot. Move upward in mass. In the range from roughly 10 to the 17 grams up to about 10 to the 22 grams, a different constraint operates. Microlensing. When a compact object passes between a distant light source and an observer, its gravity bends and amplifies the source's light in a characteristic way. Surveys watching millions of stars in the Magellanic Clouds and the Andromeda Galaxy, Eros, Macho, Ogle, and more recently the Subaru Hyper-Suprime Cam survey have searched for these lensing events. The duration of a lensing event depends on the mass of the lensing object, so different mass ranges produce events of different timescales. The surveys have found fewer events than a dark matter population of PBHS would predict in various parts of this range. Not zero events, but fewer. The constraints are not absolute, and different analyses of the same data sometimes yield different conclusions about precisely which masses are ruled out and by how much. The uncertainty is real. At higher masses still, solar mass and above, gravitational wave observations constrain the merger rate of PBH binaries. If PBHS constituted all of the dark matter at solar mass scales, LIGO and Virgo would expect to detect far more binary PBH mergers than have been observed. The current merger catalogue is consistent with a small fraction of dark matter in PBHS at those masses, but not with all of it. Above that, CMB constraints operate. Massive PBHS accreting matter in the early universe would inject energy into the photon baryon plasma, leaving distortions in the CMB spectrum and affecting the pattern of temperature fluctuations. No such distortions have been detected at the level that would be required if PBHs above roughly a few thousand solar masses constituted a significant fraction of dark matter. Cross out each range as you move through them. Low masses, Hawking evaporation constraints, higher microlensing surveys, higher still gravitational wave merger rates, and at the top CMB distortions. Write each one off the list as you go. What is left when you reach the end of this process is the asteroid mass window. Roughly 10 to the 17 grams to 10 to the 23 grams, objects with masses between a small asteroid and a large one, in black hole form. In this range, the microlensing constraints weaken because the lensing timescales become very short and are poorly sampled by most surveys. The Hawking evaporation constraints do not reach this high. The gravitational wave constraints do not reach this low. The CMB constraints require masses many orders of magnitude larger. The various observational tools that constrain every other part of the spectrum have, in this particular range, gaps that align. The window has survived every test brought to it so far. That is not the same as confirmation. I want to be careful about that distinction, because survival of constraints and positive evidence are genuinely different things. A mass range being unconstrained tells you that current instruments cannot rule it out, not that the objects are there. The absence of a constraint is not itself a signal, but it is not nothing either. 50 years of increasingly sensitive observations have closed almost every other region of the PBH dark matter parameter space. The asteroid window has remained open through all of it. Each new survey, each new analysis, each new telescope generation has pushed the boundaries of the window slightly, but has not closed it. That pattern of survival is at minimum worth taking seriously. Whether PBHs in this mass range actually exist, and in what abundance, is a question that the next generation of instruments is being specifically designed to address. Proposed mega electron-volt gamma-ray telescopes could detect the soft Hawking radiation from asteroid mass PBHs. Gravitational wave detectors, sensitive to different frequency ranges, could probe their merger rates. The window is not permanent. It will either be filled with a detection or closed by a tighter constraint. For now, it remains open. A gap in the map where dark matter could be, and where nothing has yet been able to prove it is not. That is, in the current state of knowledge, as close to a candidate as the field has. The standard picture of Hawking evaporation is clean. A black hole forms, radiates thermally, loses mass, radiates more intensely as it shrinks, and eventually, so after a time determined by its initial mass, completes its evaporation in a final burst of high-energy particles. The process is self-similar. Each stage looks like the previous stage, only hotter and faster. Nothing about the black hole's interior history changes the external thermal spectrum. The radiation carries no information about what fell in. It is pure heat, rising in temperature as the mass falls, until there is nothing left. This picture has a problem, not an observational problem. No evaporating black hole has ever been directly detected, a theoretical one. It is called the information paradox, and Hawking himself identified it in 1976, 2 years after publishing the evaporation result. If everything that falls into a black hole is eventually returned as perfectly thermal radiation, radiation with no information content beyond temperature, then the information about the original state of that matter has been destroyed. Quantum mechanics says that cannot happen. Information cannot be destroyed in quantum theory. It can be scrambled, hidden, redistributed, but not erased. The evaporation picture, taken at face value, violates a foundational principle of the theory that is partly responsible for producing it. The paradox has been argued over for nearly 50 years. Various resolutions have been proposed. Information leaking out slowly through subtle correlations in the Hawking radiation, information stored in a remnant at the Planck scale, information released in a final flash at the end of evaporation. None has achieved consensus. The problem remains genuinely open. In 2018, Georgi Diwali and collaborators proposed a framework that approached the paradox from a different direction. Their argument, which they developed through several papers over subsequent years, was that a black hole is not a featureless thermal radiator at any stage of its evaporation. It is a quantum system with memory. The information about everything that has ever fallen into it is encoded in the internal quantum state, not accessible from outside but present, stored, occupying what they described as the black hole's memory modes. The key observation was this: as a black hole evaporates and its mass decreases, the number of internal memory modes does not decrease proportionally. The information accumulated during the black hole's lifetime remains encoded in those modes, even as the mass that originally supported them drains away. At some point, roughly when the black hole has lost about half its initial mass in the simplest versions of the argument, the burden of stored information becomes comparable to the remaining mass energy of the system. The information load, in a sense, begins to resist further evaporation. Think of a tightly wound spool of wire, not locked, not fastened to anything, just wound under tension, the accumulated structure of its own wrapping, creating a resistance to unwinding that increases the more tightly packed it becomes. Nothing external is holding it closed. The resistance comes from what has been built into it. The memory burden effect is something like that. The information stored in the black hole's quantum state creating a back pressure against further mass loss, not through any classical mechanism but through the quantum energetics of the memory modes themselves. The consequence, if the framework is correct, is that evaporation does not proceed self-similarly all the way to zero mass. At some point the system stabilizes, the evaporation rate drops sharply. The black hole settles into a long-lived remnant state. Not a final burst, not a complete disappearance, but a kind of quantum stasis, in which the object retains a small but non-zero mass and continues to exist indefinitely, or at least for timescales far longer than the standard Hawking picture would permit. This was published formally in 2024 in the context of primordial black holes specifically. Thoss, Burkert and Khoury showed that if the memory burden effect operates as the Diwali framework describes, then PBHs below the standard evaporation threshold, objects lighter than about the 10 to the 15 grams, which the standard picture says should have already evaporated completely, might not have evaporated at all, or might have evaporated only partially. The mass window for surviving PBHS, which the standard Hawking picture places firmly above 10 to the 15 grams, could extend significantly downward. Objects that were thought to be gone might still be here. Whether this is correct is not established. The memory burden framework is theoretically motivated and internally consistent, but it operates in a regime, late-stage evaporation near the Planck scale, where no quantum gravity theory is fully reliable. The result depends on assumptions about the nature of the internal quantum state and the behavior of information modes that cannot currently be tested directly. Two independent groups reached broadly similar conclusions in 2024 using different approaches, which strengthens the theoretical case without confirming it observationally. What it opens, if true, is a question rather than an answer. Some of the smallest primordial black holes, objects that formed in the first fraction of a second after the Big Bang with masses far below the asteroid window, objects that the standard picture wrote off as ancient evaporants, might be present in the universe right now, not radiating significantly, not interacting electromagnetically, just there, light, stable, quantum relics of the earliest moments of existence, surviving by a mechanism that the theory of their evaporation did not initially predict. That possibility is not confirmed. It may never be, but it is no longer obviously wrong. Gravitational waves are not sound. The comparison is useful up to a point. Both involve oscillating disturbances propagating through a medium. Both carry information about their source. Both require a detector tuned to the right frequency range. But the medium is different in a way that matters. Sound moves through matter. Gravitational waves move through space-time itself, compressing and stretching the distances between points in space as they pass, at the speed of light, without requiring any medium to carry them, and without being absorbed or scattered by anything along the way. A gravitational wave produced in the first second after the Big Bang, if it had the right frequency and amplitude, would still be propagating through the universe today, carrying intact information about whatever produced it, weakened by the expansion of the universe but not distorted by anything it passed through in 13 billion years of travel. This is what makes gravitational waves the most direct observational window into the early universe that physics currently has access to. Light cannot reach us from before recombination, the epoch around 380,000 years after the Big Bang, when the universe first became transparent. Before that, the plasma was opaque to photons. The CMB is the earliest electromagnetic signal we can ever observe, a snapshot of that recombination moment and nothing earlier. Gravitational waves do not share this limitation. They pass through the recombination epoch, through the plasma era, through the radiation-dominated phase, through everything and kept going. Primordial black holes produce gravitational waves through two distinct mechanisms, and they are different enough in their physics that they probe different aspects of the formation story. The first mechanism is direct. PBHs formed in the early universe did not all form in isolation. In the dense, radiation-dominated plasma, PBHs that formed in proximity to one another could be captured into binary orbits by their mutual gravitational attraction, modified by the dynamical effects of the surrounding plasma. Over time, sometimes very long timescales, sometimes shorter ones depending on the binary parameters, these pairs would lose energy to gravitational wave emission and in spiral, eventually merging. The merger itself produces a burst of gravitational waves, similar in structure to the signals LIGO detects from stellar binary black hole mergers, but potentially at different mass scales and with a different statistical distribution of masses and spins that reflects their primordial rather than stellar origin. The population of PBH binary mergers across cosmic history would contribute a stochastic background, a superposition of gravitational wave signals from so many individual events, spread across so much of the observable universe's history, that they blur together into a continuous hum rather than discrete detectable events. The amplitude and spectral shape of this background depend on the PBH mass function, the initial clustering of PBHs at formation, and the fraction of dark matter they constitute. Different assumptions produce different predictions, which means the stochastic background is, in principle, a diagnostic tool. It encodes information about the PBH population in its shape. The second mechanism is more subtle, and in some ways more fundamental. It does not require PBH mergers. It does not even require the PBHs themselves to produce the signal exactly. It arises from the same scalar curvature perturbations that created the PBHs in the first place. When inflation ended, it left behind a spectrum of curvature perturbations, the same enhanced perturbations at small scales that we discussed in the context of the power spectrum. These perturbations source gravitational waves at second order in perturbation theory. What this means in physical terms is that two scalar perturbations can interact with each other and produce a gravitational wave as a byproduct, even though a single scalar perturbation does not produce gravitational waves at first order. The process is inefficient in the sense that the gravitational wave signal produced this way is smaller than it would be from a first-order source, but the amplitude of the scalar perturbations required for PBH formation is so large, 7 orders of magnitude above the CMB baseline, that the second-order gravitational wave signal they generate is potentially detectable. These are called scalar-induced gravitational waves, and their spectrum is tied directly to the primordial power spectrum at small scales. The peak frequency of the signal corresponds to the scale of the perturbations, which corresponds to the mass of the PBHS formed from them. If PBHS formed at the QCD scale, the induced gravitational wave signal peaks at nanohertz frequencies. If they formed at earlier times, the peak shifts upward. The signal is not a record of the PBHs themselves, it is a record of the conditions that produce them, pressed into the gravitational wave background at the moment of formation and still propagating today. Hold a railing on a large bridge in wind sometime. The vibration is almost below the threshold of sensation, not sound, not movement visible to the eye, just a faint, persistent hum felt through the palm, carrying information about the structure and the forces acting on it from somewhere far along the span. Gravitational waves from PBH formation are something like that, carrying information about their source through a medium that does not attenuate them, arriving at instruments that must be large and quiet enough to feel something that small. LISA, the Laser Interferometer Space Antenna, planned for launch in the mid-2030s, is designed specifically for the millihertz frequency band between the sensitivity ranges of existing ground-based detectors like LIGO and the nanohertz band probed by pulsar timing arrays. This frequency band corresponds to gravitational wave sources including massive black hole binaries, extreme mass ratio in spirals, and, critically, the stochastic backgrounds produced by both PBH binary mergers and scalar-induced gravitational waves from the formation era. LISA will consist of 3 spacecraft in a triangular formation, separated by roughly 2.5 million kilometers, exchanging laser beams with a precision that allows it to detect changes in arm length smaller than a fraction of the diameter of an atom. In space, away from seismic noise, away from atmospheric disturbances, with baselines measured in millions of kilometers rather than kilometers, it can access frequencies that no ground-based instrument can reach. Whether it will detect a signal attributable to primordial black holes depends on whether PBHs exist in sufficient numbers at the right mass scales. The signal predictions span a range of amplitudes that straddle LISA's projected sensitivity. Some models predict a clear detection, others predict signals below the threshold. The uncertainty is not in the instrument, it is in the source population. What LISA represents, regardless of outcome, is the first instrument with a realistic prospect of reaching back past the CMB, past recombination, past nuclear synthesis, to the formation era itself. If the gravitational wave background carries the imprint of PBH formation from the first second of the universe, LISA is the most credible tool we have for reading it. Pulsars are neutron stars that rotate. That description covers the basic fact but misses what makes them useful. The relevant detail is that they rotate with extraordinary regularity, some of them, the millisecond pulsars, spinning hundreds of times per second with a stability that rivals the best atomic clocks on Earth. Each rotation sweeps a beam of radio emission across space, and when that beam crosses the line of sight to a radio telescope, it registers as a pulse. Precise, repeatable, arriving at intervals that can be predicted to within nanoseconds over observation periods spanning years. This regularity is the instrument, not the pulsar itself, but the timing of its pulses. If a gravitational wave passes between the pulsar and the telescope, it stretches and compresses the distance between them, not visibly, not by any amount that any ruler could measure, but by enough to shift the arrival time of the pulses by nanoseconds. A pulse arrives slightly early when the wave has compressed the intervening space, slightly late when it has stretched it. Over years of observation, tracking the residuals between predicted and observed pulse arrival times, a pulsar timing array can build up a picture of the gravitational wave environment the pulses are travelling through. One pulsar gives you one line of sight, but the galaxy contains hundreds of millisecond pulsars accessible to radio telescopes. Time many of them simultaneously, and you have a distributed instrument with baselines of thousands of light years. A gravitational wave detector whose arms are longer than any human engineering could build, and whose sensors were placed there by stellar evolution billions of years ago. NanoGrav, the North American Nanohertz Observatory for Gravitational Waves, has been timing an array of pulsars since 2004. The European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Indian Pulsar Timing Array have been doing the same. In 2023, all of them, working from independent datasets, reported the same result: a stochastic gravitational wave background at nanohertz frequencies, not a single event, not a point source, a background hum present in all directions, with a characteristic spectral shape consistent with what gravitational wave theory predicts from a population of sources distributed across the observable universe. The most natural explanation for a nanohertz stochastic background is supermassive black hole binaries, pairs of black holes with masses billions of times the Sun's mass, orbiting each other at the centers of merging galaxies, losing energy to gravitational wave emission over millions of years. The population of such binaries across the universe, integrated over cosmic history, should produce exactly this kind of background. And the signal detected by the pulsar timing arrays is broadly consistent with that expectation. Broadly, not perfectly. The spectral shape of the observed background, the way its amplitude changes with frequency, shows features that the supermassive black hole binary explanation does not fully account for. The signal is somewhat louder at the low frequency end than the standard binary population models predict. Several alternative or additional sources have been proposed to explain the excess, among them a stochastic gravitational wave background from bubble dynamics during a first-order cosmological phase transition. A first-order phase transition proceeds through the nucleation and expansion of bubbles of the new phase within the old one, like bubbles forming in a liquid approaching a boil, but occurring in the quantum fields of the early universe. As the bubbles expand and collide, they produce gravitational waves. The amplitude and spectral peak of those waves depend on the temperature at which the transition occurred. A transition occurring near the QCD confinement scale, around the temperature and time of the quark-hadron transition that we spent time with in Chapter 10, produces a gravitational wave background peaking at nanohertz frequencies, which is exactly the frequency range the pulsar timing arrays are sensitive to. The connection to primordial black holes is this: a strongly first-order QCD transition, one vigorous enough to produce a detectable gravitational wave background, would also be the kind of transition that most dramatically enhances PBH formation. The softening of the equation of state that creates the formation window for solar mass PBHs is directly related to the thermodynamics of the transition. A more violent transition means more softening, a lower collapse threshold, more black holes formed. The gravitational wave signal and the PBH population would be two consequences of the same underlying physics. Whether the nanograv signal is actually telling us something about PBH formation is not, this needs to be said plainly, established. The supermassive black hole binary explanation remains viable, and in many analyses remains the most probable single source. The first-order phase transition interpretation requires a transition more strongly first-order than the QCD transition is currently believed to be in the standard model of particle physics, which means it would require new physics beyond what we know. That is possible. It is not confirmed. But the timing arrays have been running for decades. Some of the pulsars in the NanoGrav catalogue have been timed since the mid-1980s. All those years of nanosecond measurements, all that quiet accumulation of residuals against predicted arrival times, and the signal that emerged from it is consistent under certain assumptions with the gravitational echoes of a phase transition that happened 1 microsecond after the Big Bang and produced the black holes we have been discussing for the last several chapters. There is something specific about that, a clock running in another room, unattended, measuring something you did not know it was measuring for longer than you thought to ask what it was doing. The arrays are still running, the dataset is still growing. Whether the signal resolves toward a primordial interpretation or away from it will depend on what the next decade of timing produces. On the 12th of November 2025, 3 gravitational wave detectors registered a signal. LIGO Hanford in Washington State, LIGO Livingston in Louisiana, Virgo outside Pisa, 3 separate instruments on 2 continents, each independently measuring the same distortion in space-time as it passed through Earth at the speed of light. The signal lasted a few tenths of a second in the detector's sensitive band, a brief chirp, rising in frequency and amplitude as the 2 objects producing it spiraled inward and merged. The detectors logged it. The automated pipelines processed it, and the collaboration, working through its standard candidate event protocol, catalogued it under the designation S251112CM. This is how every detection begins. A signal, a catalog entry, an analysis pipeline working through the data to extract what parameters can be extracted. The procedure is the same whether the event is routine or not. And by late 2025, gravitational wave astronomy had accumulated enough detections. The JWST 5.0 catalog, released in May 2026, documents 390 confirmed events that the procedure had become genuinely routine. Most events are binary black hole mergers, some are binary neutron star mergers, a few are mixed. All of them in the confirmed catalogue involve objects whose masses are consistent with what stellar evolution produces. S251112CM was different in one specific way, not in how it was detected, not in the quality of the signal, in the mass. The chirp mass of a binary system, the combination of the 2 component masses that gravitational wave observations measure most precisely, fell predominantly in the range between 0.1 and 0.87 solar masses. That range is not a wide uncertainty band reflecting poor measurement quality. It reflects the actual posterior probability distribution across a genuine parameter space constrained by the signal's phase evolution. The probability that at least one of the 2 merging objects had a mass below 1 solar mass was assessed at greater than 99%. Subsolar, that is the word the analysis kept returning to. One or both of the objects in this merger weighed less than the Sun, which sounds, stated plainly, like a detail. It is not a detail. It is the entire diagnostic. Here is why. The Sun has a mass of approximately 2 times 10 to the 30 grams. Stars that eventually produce black holes through core collapse are significantly more massive than the Sun, at minimum several solar masses, typically between 8 and 100 solar masses for the standard stellar evolution pathways that produce stellar mass black holes. A star cannot collapse into a black hole if it is too light. There is a minimum mass required, set by the physics of nuclear burning and core collapse, and the Chandrasekhar limit and the properties of neutron degeneracy pressure. Below a certain mass threshold, a collapsing stellar core does not have enough gravity to overcome neutron degeneracy pressure. It becomes a neutron star, not a black hole. The lower mass limit for a stellar origin black hole is approximately 3 solar masses, from the Tolman-Oppenheimer-Volkoff limit on neutron star mass. Some analyses push this slightly, some pull it, and there is genuine theoretical uncertainty at the boundary between the heaviest possible neutron stars and the lightest possible stellar black holes. But nowhere in the serious literature on stellar evolution is there a mechanism that produces a black hole from a stellar progenitor with a mass below 1 solar mass. There is no model, there is no pathway, the physics simply does not permit it. A neutron star can be subsolar in mass. The lightest confirmed neutron stars sit around 1.1 or 1.2 solar masses, with theoretical lower limits somewhat below 1 solar mass depending on the equation of state. So one interpretation of S251112CM is that it involved a neutron star rather than a black hole, a subsolar neutron star merging with a compact companion. That interpretation is not ruled out by the gravitational wave signal alone, but there was no electromagnetic counterpart, no kilonova, no gamma-ray burst, no optical transient detected in follow-up observations across the roughly 1700 square degrees of sky localization that the three-detector network produced. Binary neutron star mergers and neutron star black hole mergers, when they produce electromagnetic emission, do so through the ejection of neutron-rich material that synthesizes heavy elements and glows across optical and infrared wavelengths for days to weeks. The absence of a counterpart does not prove the merger involved no neutron star. It makes it less likely. A confident neutron star merger with no electromagnetic signal is possible, but requires the geometry or the viewing angle, or the merger dynamics to conspire against detectability in ways that are not the expected outcome. The remaining interpretation, the one that a merger involving at least one subsolar mass black hole most naturally points to, is an origin that has nothing to do with stellar evolution, an object that formed not from a dying star but from a density fluctuation in the early universe, an object that acquired its mass not through billions of years of nuclear burning and gravitational accumulation, but from the size of the Hubble horizon, at the moment a collapsing region crossed the density threshold. A primordial black hole carrying a mass below one solar mass because it formed before the first second of the universe's existence, when the horizon mass was in precisely that range. The source distance was estimated at 93 megaparsecs, give or take 27, roughly 300 million light-years. The false alarm rate was initially assessed at approximately 1 in 6 years, later refined to 1 in 4 years. Neither number is negligibly small. The event is a candidate, not a confirmed detection in the sense that catalogue entries are confirmed after full parameter estimation and peer review. As of the data available at the time of this recording, S251112CM had not yet been formally incorporated into a published gravitational wave catalogue. What it had done was generate two independent theoretical analyses, both pointing in the same direction. Subsolar mass, no stellar explanation, no electromagnetic counterpart. The signal sits in the data, waiting. Two research groups, working independently, looked at S251112CM and asked the same question. If this signal came from a primordial black hole merger, what does that imply about the PBH population as a whole? The first study came from Alberto Magaraggia and Nico Capilouti at the University of Miami, published in the Astrophysical Journal in March 2026. Their approach was to work backward from the detection, or candidate detection, to the underlying PBH mass function that would need to exist in order to make such an event plausible. They used the LIGO-Virgo-Cagra network's detection sensitivity, the estimated distance to the source, and the mass parameters extracted from the signal to constrain what fraction of dark matter could be in the form of PBHS at the relevant mass scales, and what merger rate that fraction would predict for future observations. The predicted rate they arrived at was approximately 0.8 detectable subsolar PBH merger events per year, with the current LIGO-Virgo-Cagra network at its current sensitivity, not 0.8 per decade. Per year, which is a number that carries a specific implication. Events in this mass range should be rare, but not vanishingly so. If the PBH interpretation of S251112CM is correct, the network should, over a long enough observing campaign, detect more of them. Not routinely, not frequently, roughly 1 every 14 months or so on average, with the statistical scatter that comes with Poisson processes and varying detector sensitivity across observing runs. 1 every 14 months is consistent with the observed situation. One candidate event, ESSA 2-51112CM, in a dataset spanning the first 4 observing runs. The rarity is not evidence against the interpretation. If anything, the rarity is what the model predicts. A population that produces one confirmed detection in several years of observation is not a population that was missing from the data. It is a population that was always expected to be sparse. The second study from Hack, Iocco and Vicinelli, published on ArcCD in March 2026 within days of the Miami paper, took a different modelling approach. Rather than anchoring to the specific properties of S251112cm and working backward, they approached the question from the PBH formation side, constructing a mass function from theoretical priors about PBH formation in the early universe, and asking what gravitational wave detection rate that function would predict across the full Li, GO, Virgo, KAGRA sensitivity range. Their conclusions were broadly similar. The PBH dark matter fraction, implied by a detection rate consistent with S251112cm, sits in a range that does not require PBHS to constitute all of dark matter, but does require them to constitute a meaningful fraction. Their modelling suggested approximately 4% of dark matter could be in the form of PBHS in the relevant mass range, with the uncertainty spanning roughly an order of magnitude in either direction depending on formation model assumptions. When two groups arrive at the same destination through different routes, the result carries a quality that no single calculation possesses. Not confirmation. Confirmation requires observational verification, and that has not happened, but a kind of structural robustness. The Miami team started from the detection and asked what population it implied. The second team started from the population and asked what detection rate it predicted. They met somewhere in the middle. That convergence is not proof of anything. It is, however, harder to dismiss than a single analysis would be. The JWST 5.0 catalogue, released by the LIGO Virgo CAGRA collaboration in May 2026, provides the clearest context for what makes S251112cm unusual. The catalogue documents 390 confirmed gravitational wave detections, covering events from the first observing run through January 2025. Among those 390 events, binary black hole mergers, binary neutron star mergers, and mixed systems, not one involves a confirmed subsolar mass component. Not one. Every component mass in every confirmed event is consistent with stellar evolution. The catalogue in this respect is entirely conventional. S251112cm sits outside that catalogue. Detected in November 2025 after the catalogue's end date, not yet formally processed through the full parameter estimation and peer review pipeline that converts a candidate event into a catalogue entry. It exists, at the moment of this recording, as a candidate, a signal with a false alarm rate of roughly 1 in 4 years, a subsolar chirp mass, no electromagnetic counterpart, and 2 independent theoretical analyses suggesting a primordial black hole interpretation is physically coherent. What the signal tells us, if genuine, is something specific about the mass function. PBHs in the subsolar range, objects that could only have formed in the first second of the universe, must exist in sufficient abundance to produce approximately 1 detectable merger per year. That abundance is consistent with a dark matter fraction of a few percent at those mass scales. Not all of dark matter, not a negligible fractions either. Something in between, in a mass range that overlaps with the window left open by the constraint survey discussed in the Asteroid Window chapter, though at somewhat different scales. What it does not tell us, and cannot tell us from a single event, is whether the primordial interpretation is uniquely correct. A subsolar mass object is necessary evidence for a non-stellar origin, but it is not sufficient evidence to distinguish between all possible non-stellar formation channels. Other exotic compact objects, stable configurations of scalar fields, so-called boson stars, certain classes of exotic stellar remnants, could in principle produce subsolar mass mergers. The PBH interpretation is the most theoretically developed and most naturally motivated candidate. It is not the only candidate. S251112cm is, within the current gravitational wave catalogue, categorically singular. 390 confirmed detections, each consistent with stellar evolution. One candidate sitting just outside the catalogue boundary, consistent with something older. Whether it becomes the first entry in a different kind of catalogue entirely depends on what the detectors find next. In the local universe, in the galaxies close enough that we can study them in detail, there is a relationship between the mass of the supermassive black hole at a galaxy's centre and the mass of the galaxy's stellar bulge. Not a perfect relationship, not a law written with the precision of orbital mechanics, but a correlation tight enough found in enough galaxies across enough different survey methods that it has come to be treated as a fundamental feature of how galaxies and their central black holes co-evolve. The ratio of black hole mass to stellar bulge mass in nearby galaxies clusters around roughly 1 part in 1,000. A galaxy with a stellar bulge of 100 billion solar masses tends to host a central black hole of around 100 million solar masses. The numbers vary, the scatter is real, but the relationship holds across orders of magnitude in galaxy mass, with enough consistency that departures from it are informative rather than routine. The James Webb Space Telescope, since its science operations began in 2022, has been finding departures. Not small ones. Not departures that sit within the scatter of the local relation and require careful statistical argument to establish. Departures by factors of 10, 50, 100. Galaxies at redshifts above 7, meaning we are seeing them as they existed less than 800 million years after the Big Bang, hosting central black holes whose masses are a substantial fraction of the galaxy's entire stellar mass, not 1,000th of it. Black hole to stellar mass ratios that would be extraordinary outliers in the local universe appearing, in the early universe, as something closer to a population. The objects that display this most dramatically have been grouped under an informal designation, little red dots. The name comes from their appearance in JWST imaging, compact, faint red in the infrared bands, with spectroscopic signatures revealing broad emission lines characteristic of actively accreting black holes. They are not rare in the JWST data. They appear in multiple survey fields at multiple redshifts between roughly 4 and 11, in numbers that were not predicted by models calibrated on the local universe. What makes the little red dots genuinely difficult to explain is not the black holes themselves. A sufficiently massive black hole seed, given enough time and enough gas to accrete, will grow. The problem is the time. At redshift 7, the universe is approximately 750 million years old. A black hole that needs to reach, say, 100 million solar masses by that epoch had to get there in under 800 million years starting from whatever it was born as. If it started from the remnant of a population 3 star, the standard light seed scenario, it was born with a mass somewhere between 100 and 1,000 solar masses. Growing from 1,000 solar masses to 100 million solar masses requires gaining a factor of 100,000 in mass. At the Eddington limit, the maximum accretion rate permitted by radiation pressure, a black hole doubles its mass on a timescale of roughly 45 million years. To gain 5 factors of 10 from 1,000 solar masses to 100 million, accreting continuously at the Eddington limit takes roughly 500 million years. That barely fits inside the available time, with no margin for the periods of reduced accretion that observations of real accreting black holes show are common. Push the target mass higher, or the starting mass lower, and the arithmetic stops working. There is a specific feeling that comes from redoing a calculation and getting the same answer. Not satisfaction. Something closer to the mildly unsettled quality of a number that will not move no matter how you approach it. The time constraint for early black hole growth has that quality. It has been checked many times by many groups, with different assumptions about accretion physics, seed formation, and merger histories. The conclusion does not change much. The most massive early black holes that JWST is finding are difficult to produce through standard pathways in the available time. The ratio problem compounds this. In the local universe, the tight correlation between black hole mass and stellar mass is thought to reflect a long history of coevolution, the black hole and the galaxy growing together, regulating each other through feedback processes, with the black hole's energy output periodically suppressing star formation and the star formation history shaping the conditions for accretion. This coevolution takes time. It requires many cycles of accretion, feedback, and star formation across billions of years. The local relation is, in a sense, the endpoint of a long process. The little red dots show black hole to stellar mass ratios that are not the endpoint of coevolution. They show ratios where the black hole is already enormous relative to the galaxy. At an epoch when the galaxy should still be in early stages of assembly, the black hole is not 1,000th of the stellar mass. In some cases, it is close to the stellar mass itself, or even comparable to it. The ledger does not balance. The black hole is too heavy for the galaxy around it. At a time when the galaxy has not had enough time to grow to match it, this is not, and I want to be careful about this word, this is not a crisis in cosmology. It is not a sign that the standard model of structure formation is fundamentally broken. It is a genuine challenge, but the kind of challenge that science absorbs and responds to rather than collapses under. Several explanations have been proposed. Super-Eddington accretion, in which black holes grow faster than the standard radiation pressure limiter would allow through specific disk geometries or magnetic field configurations. Heavy seeds, in which the first black holes were born much more massive than population 3 stellar remnants. Direct collapse black holes, forming from the direct collapse of massive gas clouds without passing through stellar stages. And one other possibility, which connects back to everything that has come before in the story. Black holes that were not born from anything that happened in the last 13 billion years of cosmic evolution, but from a density fluctuation in the first second of the universe's existence. Seeds that were already present before the first star formed, before the first galaxy assembled, waiting in the dark for the matter of the early universe to fall toward them. Whether that is the answer for the little red dots is what the next 2 chapters address. The standard story of black hole growth begins with a star. A massive star forms from a collapsing gas cloud, burns through its nuclear fuel over a few million years, and at the end of its life collapses inward. If it is massive enough, the collapse produces a black hole rather than a neutron star. That black hole then sits in its environment, accreting whatever gas or matter comes within its gravitational reach, growing over time, possibly merging with other black holes as galaxies collide and their central objects sink toward each other. The story is long. It requires stars to form first, which requires gas to cool and collapse, which requires the universe to have expanded and cooled enough for that cooling to happen. The earliest any of this begins, in the most favourable models, is a few 100 million years after the Big Bang. A massive primordial black hole did not wait for any of that. There is a specific quality to something that was already in place before the activity around it began. A foundation stone cut and laid before the walls were raised, before the rooms were designed, before anyone decided what kind of building it would be. The stone does not announce its age. It sits there, supporting whatever was built above it, and the building does not know the difference. A massive PBH forming in the first second of the universe occupied something like that position. It was a gravitational anchor in a universe that had not yet formed a single star, a single atom, a single molecule. Everything that subsequently fell toward it did so because it was already there, already warping the surrounding space-time, already beginning the slow accumulation that would, over billions of years, produce something that JWST could eventually image. The seeding scenario works through straightforward arithmetic, which is part of what makes it worth taking seriously. Start with a PBH forming during the QCD transition. A mass near 1 or 2 solar masses, formed at 10 microseconds, sitting in the expanding plasma as the universe cools around it. Over the following hundreds of millions of years, as the universe transitions from the radiation-dominated era through matter domination, dark matter halos begin assembling around density peaks in the distribution. A PBH, being itself a density concentration, acts as an early seed for halo formation. The dark matter halo that assembles around it forms earlier and grows more massive than it would in the absence of the seed, because the PBH provides an initial gravitational well for the surrounding matter to fall into. When baryonic matter, ordinary gas, hydrogen and helium, eventually falls into these halos, it finds a black hole already waiting at the centre. Accretion begins, not super Eddington accretion, not any exotic high-rate process that requires special disk physics or magnetic field configurations. Standard sub-Eddington accretion at modest efficiency, the kind that black holes are observed to sustain throughout cosmic history in ordinary galactic nuclei. At the Eddington rate, a black hole doubles its mass every 45 million years. Starting from one solar mass at a few 100 million years after the Big Bang and accreting at a fraction of the Eddington rate, 30%, 50% varying with gas availability, and running that forward to redshift 7 produces a black hole mass in the range of tens of millions to hundreds of millions of solar masses, which is precisely the range that JWST is finding. Not through coincidence, through compound interest on an early deposit. The PBH that formed at 10 microseconds and began accreting modestly at a few 100 million years had an advantage over any black hole that had to wait for a population 3 star to live and die first. That advantage is measured in hundreds of millions of years of additional accretion time, in a universe where doubling timescales are measured in tens of millions of years. Hundreds of millions of years of head start produces factors of 10 to 100 in final mass. That factor is precisely the gap between what standard models predict for early black hole masses and what JWST observes. What the PBH seeding scenario does not require is worth stating explicitly, because it is the thing that distinguishes it from other proposed resolutions. It does not require super Eddington accretion. It does not require any departure from the standard Eddington limit physics that governs accretion in every well-studied galactic nucleus we know of. It does not require the gas supply to be continuous or perfectly efficient. It does not require any new physics beyond what the formation story itself already involves. The scenario's resolution to the JWST anomaly comes entirely from the timestamp, from the fact that PBHS formed before the structures they now inhabit, giving them an accretion head start that nothing produced by stellar evolution can match. There is also a natural explanation for the black hole to stellar mass ratios that the little red dots display. A PBH seed at the centre of a young halo began accreting gas before that gas had cooled and fragmented into stars. The black hole was growing before the stellar population was. The feedback from the accreting black hole, the radiation and outflows it produced, suppressed star formation in the surrounding gas, keeping the stellar mass low while the black hole mass grew. The result is a system where the black hole is disproportionately massive relative to the stars, not because the stars were destroyed or displaced, but because they were never given the conditions to form at the same rate the black hole was accreting. Whether this scenario is the correct explanation for the JWST observations is not established. The observations are real. The mechanism is physically coherent. The arithmetic works without requiring exotic physics. What is missing is a direct identification, a specific system where a PBH origin can be demonstrated rather than inferred. One system may be closer to that demonstration than any other. Abell 2744 is a galaxy cluster, massive, well-studied, located roughly 3.5 billion light-years away, close enough that gravitational lensing by the cluster amplifies the light from objects behind it, effectively turning the cluster into a natural telescope for observing the more distant universe. JWST has used this lensing effect extensively, and among the objects revealed behind Abell, 2744 is one that has drawn sustained attention, a compact source designated QS01, sitting at a redshift of approximately 7. At redshift 7, we are seeing the object as it existed roughly 750 million years after the Big Bang. That is not an unusual redshift for JWST observations. The telescope was specifically designed to reach this epoch and beyond. What makes Abell 2744-QS01 unusual is not where it sits in time, but what it contains, and in what proportions. The object is small, compact in the sense of being spatially unresolved or barely resolved even with JWST's angular resolution, implying a physical size smaller than typical high redshift galaxies. It is red in the infrared bands characteristic of the little red dot population, with broad emission lines confirming the presence of an actively accreting black hole at its centre. Its stellar mass, the total mass of stars in the system, has been estimated at somewhere around 10 to the 8 to 10 to the 9 solar masses, depending on the stellar population model applied. Its central black hole mass, inferred from the broad emission line widths using standard virial techniques, is comparable to, or in some estimates exceeding, the stellar mass of the entire system. That ratio, that is the thing that resists easy explanation. A black hole mass comparable to the stellar mass of its host galaxy is not just an outlier in the local black hole to stellar mass relation. It is off the local relation by a factor that the scatter in that relation cannot absorb. In a nearby galaxy hosting a black hole at the standard ratio of 1 to 1,000, a stellar mass of 10 to the 9 solar masses would correspond to a central black hole of around 1 million solar masses. Abell 2744-QS01 appears to host something orders of magnitude above that, in a system that has not had the time or the stellar mass to explain it through conventional co-evolution. The metallicity adds a second constraint, and in some ways a sharper one. Metal content, the abundance of elements heavier than hydrogen and helium in a galaxy's gas and stars, is a direct record of how much stellar processing has occurred. Stars produce heavy elements through nucleosynthesis and distribute them through stellar winds and supernova explosions. A galaxy that has hosted many generations of stars over a long period of star formation will be metal-rich. A galaxy that is young or that has suppressed its star formation will be metal-poor. Abell 2744-QS01 is unusually metal-poor for a system at its redshift. The gas and stellar population show heavy element abundances well below what you would expect if the black hole had grown through a long history of co-evolution with active star formation. A metal-poor system with a massive central black hole and a low stellar mass is almost a self-contradiction under the standard co-evolution picture. If the black hole grew through accretion alongside star formation, the star formation should have enriched the surrounding medium. The low metallicity says the enrichment did not happen or happened less than expected. The high black hole mass says the accretion did happen or happened more than the stellar record implies. The ledger is internally inconsistent unless the black hole's growth was substantially decoupled from the galaxy's star formation history. Simulations specifically targeting Abell 2744-QS01 with a massive PBH seed were published by Zhang, Liu and Brom in late 2025 and updated in early 2026. Their approach was to run hydrodynamic simulations of early galaxy formation anchored on a PBH seed with an initial mass in the range of tens of thousands of solar masses, sitting at the centre of a dark matter halo at high redshift, and track the system's evolution forward to redshift 7. What they found was that a PBH seed of sufficient initial mass could reproduce the observed properties of Abell 2744-QS01 within the current measurement uncertainties: the black hole mass, the stellar mass, the compact morphology and the low metallicity. The low metallicity is particularly informative here. In the simulation, the PBH seed began accreting gas before significant star formation had occurred in the halo. The radiation from the accreting black hole suppressed star formation in the surrounding gas, heating it, ionizing it, preventing it from cooling and fragmenting into stars at the rate it would have without the central source. The result was a system where the black hole grew substantially before the stellar population did, keeping the metallicity low because fewer stellar generations had occurred and producing a black hole to stellar mass ratio far above the local relation because the black hole had a head start measured in hundreds of millions of years. The fit is not perfect. No simulation of this kind is, given the uncertainties in the observed properties and the range of assumptions required to run the model. Different initial PBH masses, different halo masses, different accretion efficiency assumptions produce somewhat different outcomes. The result is not a proof. It is a demonstration that the mechanism is capable of producing a system like Abell 2744-QS01 without requiring super Eddington accretion, without requiring exotic physics, without requiring any departure from what PBH formation theory already predicts. There is something specific about studying one object in enough detail to say something precise about it. Not a population, not a statistical trend. One object at a specific redshift with specific properties that a specific mechanism can reproduce. It is not the same as confirmation, but it is further than inference. It is the point where theory and observation are touching. S251112 is still a candidate. That word carries weight in gravitational wave astronomy. A candidate event has passed initial detection pipelines, has a false alarm rate low enough to warrant serious analysis, and has been examined by theoretical groups who find it physically coherent. But it has not completed the full parameter estimation and peer review process that converts a candidate into a catalogue entry. And as of the time this was written, it had not been formally incorporated into any published gravitational wave event catalogue. Whether it will be, and what the final parameter estimates will say when the full analysis is complete, is not known. That uncertainty is not a flaw in the science. It is the science, operating as it should. A detection claim without full analysis and independent scrutiny is exactly the kind of claim that should remain provisional. The LIGO-Virgo-CAGRA collaborations process for converting candidates into confirmed detections is deliberate and conservative, and that conservatism has served the field well. The first binary black hole merger, GW150914, was announced with full parameter estimation and peer-reviewed analysis. Every catalogue entry since has gone through the same process. S251112CM will too, if it survives the scrutiny. Whether it survives is genuinely unknown. Hawking radiation has never been directly detected. This is not a new situation. The prediction is 50 years old and observationally unconfirmed for the entirety of that time. But it is worth stating plainly in a chapter about what remains unproven, because Hawking radiation is not a peripheral claim. It is foundational to everything discussed in the evaporation chapters. The temperature of a black hole, the relationship between mass and lifespan, the critical mass of 5 × 10⁻14 grams for present-era evaporation, all of it rests on a theoretical result whose direct observational confirmation has so far eluded every instrument deployed to find it. Gamma-ray searches for evaporation bursts have set upper limits on the local abundance of near-critical mass PBHs. Those limits are informative. They are not detections. The dark matter fraction is bounded but not pinned. Existing constraints tell us that PBHS cannot constitute all of dark matter at most mass scales, and the asteroid window remains the primary unconstrained region where 100% dark matter fraction in PBHS is still permitted. But permitted is not the same as measured. The actual fraction, whether it is 1%, 10%, or something approaching the full dark matter budget in some mass range, is not known from direct observation. The theoretical analyses motivated by S251112CM suggest a few percent at subsolar masses, but those analyses are themselves contingent on the primordial interpretation of a single unconfirmed candidate event. The uncertainty propagates in both directions. The nanograv signal has not resolved into a definitive source identification. The stochastic gravitational wave background at nanohertz frequencies is real. That is now well established across multiple independent pulsar timing array datasets. What produced it remains an open question. Supermassive black hole binaries remain the most thoroughly developed explanation. The first-order phase transition interpretation, which would connect the signal to PBH formation at the QCD scale, requires a transition more strongly first-order than the standard model of particle physics predicts. More data from the arrays, and the datasets are growing year by year, as more pulsars are timed with increasing precision, will constrain the spectral shape of the background more tightly and may eventually distinguish between source populations. Eventually is doing real work in that sentence. There is a specific patience that this field requires, not the patience of waiting for a technology that does not yet exist. LISA will launch. The Pulsar timing arrays will accumulate decades more data. Next-generation ground-based detectors with greater sensitivity are in planning, but the patience of setting a question down and accepting that the answer will arrive on the schedule imposed by the universe's faintness at cosmological distances, not on any schedule we would prefer. The instruments being built are the right instruments. The questions are well posed. The weighting is structural, not contingent. The Abell 2744-QS01 simulations show that a PBH seed can reproduce the object's observed properties. They do not show that a PBH seed is the only mechanism that can. Direct collapse black holes, heavy seeds from stellar collisions in dense early clusters, runaway accretion in specific gas environments, these remain viable alternatives for at least some of the JWST anomalies. The PBH scenario has the advantage of naturalness. It does not require any additional physics beyond what PBH formation already invokes, and it sidesteps the time constraint problem through the head start mechanism rather than by invoking exceptional accretion rates. But naturalness is not evidence. It is a property of a model's internal structure, not a property of the universe. What the field has, honestly assessed, is this: a physically coherent formation mechanism for objects that no other process produces, a detection candidate with the right mass signature and no electromagnetic counterpart, a gravitational wave background compatible with the expected imprint of phase transition era PBH formation, a JWST anomaly that PBH seeding resolves without exotic physics, simulations of a specific object that fit the observations within current uncertainties. None of those things, individually or together, constitute proof. They constitute a case, a set of lines of evidence pointing in the same direction, each independently motivated, none individually decisive. Whether proof arrives, and through which instrument, and when, that is what the next decade of observation is for, and the questions are not failures. They are the exact shape of what remains to be learned. There are valleys on Earth shaped by rivers that no longer exist. You can stand in one and read the whole story from the landscape, the curve of the walls, the gradient of the floor, the way the tributaries meet, and this river itself is gone. Dry for 10,000 years, or 100,000. What organized the valley is absent. What it left behind is the entire visible structure of the place, and you would not understand the place at all without accounting for something you cannot see. The cosmic web may be like that. The filaments of dark matter and gas that connect galaxy clusters across hundreds of millions of light years. The nodes where clusters sit, massive and hot, filled with plasma that took billions of years to accumulate. The voids between the filaments, regions so empty that a photon can travel across them for hundreds of millions of years without encountering significant matter. All of this large-scale structure grew from seeds, from the initial density fluctuations that inflation froze into the fabric of the early universe, the ones that re-entered the Hubble horizon and either dispersed as acoustic waves or collapsed into the first gravitational wells. The cosmic web is not random. It is the evolved consequence of a specific initial pattern imprinted before the first second of the universe's existence. Whether primordial black holes contributed to the organization of that pattern is not a settled question, but it is a serious one, and the seriousness of it has grown over the past few years in ways that the evidence described across these chapters reflects. PBH's forming in the first millisecond would have introduced additional density concentrations into the matter distribution of the early universe, concentrations that did not require the slow cooling and fragmentation of gas clouds that normal structure formation needs. They were there first, already present in the radiation plasma, already warping the surrounding space-time, already providing gravitational anchors for the dark matter halos that would later assemble around them. Whether the largest structures in the observable universe bear the fingerprints of that early architecture, whether the particular arrangement of filaments and voids and clusters carries some imprint of PBH formation events from the first millisecond, is something that current observations cannot directly confirm, and current simulations are only beginning to address, but the question is physically motivated. It is not speculation layered on top of speculation. It follows from mechanisms that have been worked through carefully, from formation physics that is anchored in general relativity and quantum mechanics, from observations, JWST, the Pulsar timing arrays, the LIGO candidate, that are each independently pointing toward early universe objects that no conventional stellar process produces. What this story adds up to, if you follow it from the beginning, is something that feels counterintuitive but becomes more natural the longer you sit with it. The objects we know best, stars, planets, galaxies, the structures built from stellar evolution and gravitational accumulation over billions of years, may have formed inside a framework that was already partially in place. The cosmic web's earliest skeleton, the first gravitational wells that matter fell toward, the seeds of the most massive structures we can observe, some fraction of all of that may trace back not to the cooling of gas or the death of stars, but to density fluctuations that crossed a threshold in the first millisecond, and collapsed before the universe had decided what it was going to become. There is a particular quality to objects that shape something enormous without being seen. The scaffolding that comes down once the structure can hold itself, the current that carved the canyon and then dried. Primordial black holes, if they are what the evidence is increasingly suggesting they might be, are that kind of object. They would have been present at the beginning, active in the early universe in ways that influenced the distribution of matter for billions of years afterward, and yet invisible to every telescope pointed at the sky before JWST and LIGO brought us close enough to the edge of what they left behind to start making out the shape of it. The ones that formed with masses above the evaporation threshold are still here, some in the asteroid mass range, possibly constituting a fraction of the dark matter that fills galactic halos, some at solar masses, possibly producing merger events that gravitational wave detectors are only now beginning to find, some more massive still, possibly sitting at the centres of the earliest galaxies as the seeds from which supermassive black holes grew, feeding quietly in the dark for hundreds of millions of years before the first star formed anywhere in their vicinity. And the ones that formed below the evaporation threshold are gone, unless the memory burden effect preserved them in ways the standard picture did not predict. If it did, they are here too, small, cold, stable, quantum relics carrying information about the first moments of the universe in a form that nothing else preserves. The first millisecond produced them, in a plasma so hot that matter and energy were the same thing, in density fluctuations that quantum mechanics made inevitable, in the brief softening of phase transitions that let gravity win where it almost never wins, in the closing of a trap that the geometry of the Hubble horizon built and radiation pressure could not hold open. What followed was everything else, every star, every galaxy, every cluster, every void. 13 billion years of structure assembling itself in a universe that had already, in its first millisecond, laid something down. Whether we will ever see that laying down directly, whether the gravitational wave background will resolve into a clear primordial signal, whether the asteroid window will yield a detection, whether the subsolar LIGO candidate will become a confirmed catalogue entry, is what the next decade of observation will determine. For now, the architects are in the dark, patient, permanent, waiting for instruments precise enough to read what they left behind. Thank you to everyone who supports the Sleepy Physicist on Patreon. Because of you, this episode was made possible.